and said, what's going on? And apparently they'd noticed it from experiments in the 1950s. It wasn't understood. Fleischmann didn't understand it. And what he told me is in the paper that involved this research but didn't give the calorimetric measurements for the errors from around 1972. So between 1972 and early 1980s, he had time to stew about it. And basically he thought, well, with deuterium in, maybe the chemistry of deuterium is a little bit like it's like hydrogen, except it's nuclear. Chemistry of nuclear reactions is like chemical reactions, except the barrier is a little bit bigger and the energy is a little bit larger. So his point of view was maybe the deuterium was involved in the process of something. But he thought, well, if something like that's true, you need a bigger than a 1% effect. So the brainstorm, Fleischmann's brainstorm was to say, let's go ahead, let's set the system up, let's look at deuterium, and let's poke it, tweak it, just beat on it, and see if we can get the 1% effect turn it into a 2% effect. We get the 2% effect turn it into a 5% effect. So according to Fleischmann, that's what the early research was about. In fact, they managed to tweak it into a 5 and 10% effect. And they kept on going. He also noticed back in the early days of the early 1980s that the discrepancy, the anomaly, was always positive. It was always a little bit more energy than would have corresponded to an accurate 10%. Thank you for a fantastic question. Did you have a question?
Well, it was just a minor question. Back in your description of the configuration of the original cell, you said there was a reference cathode that was also plugged in. So there were two cathodes in the cell. Because I don't, of course, the anode was platinum, I think, but if I recall.
The anode's platinum.
I think it was a subsequent slide.
Okay. Reference electrode.
Okay.
This thing's pointing at this guy, right? Maybe this is the reference connection.
And I think maybe I saw it on the subsequent slide.
Yeah, when you look at the materials that are involved.
Yeah,
Yeah,
well,
sure.
there was a reference. There was a reference electrode in it, and basically,
Okay.
so the idea is that in order to get some assessment of how much deuterium is in the palladium, Fleischmann checked the voltage of the reference electrode against the cathode, and he used that as a way to figure out how well he was doing. That reference electrode is going to become important for us a little bit later. Okay, let's so
One
implication.
more question.
Oh, yeah.
You said there were no, there was no radiation effect. Was that measured, or was that just because they didn't keep the bucket?
The thing I don't remember, if Fleischmann explained it to me, is what kind of tests they did early on for radiation. Now, the issue of radiation became extremely important much later on, and so it's been tested many times. I know that Fleischmann had a sodium iodide detector to look for gammas. So the idea is that if you make neutrons, the neutrons recombine into some gammas. And he misreported the signal when there was a noise in his sodium iodide detector that he interpreted as a 2.2 or maybe a gamma from neutron-proton recombination. So he got hammered and beaten on the head for that. And then 2 years later, he got a germanium detector and calibrated properly and showed the signal. By that time, nobody was listening. So implications. If you could make energy with of a nuclear origin without nuclear radiation, you've got a clean nuclear energy source. A clean nuclear energy source will solve an awful lot of the problems facing the planet. For example, there are people that have been noticing that the atmospheric CO2 has been rising in this recent CF 400 parts per million, whereas some time ago, years and years ago, it was under 300 parts per million. They're concerned about that. The idea being CO2 is thought to be a greenhouse gas. And my friends point out that water is a much bigger greenhouse gas because when you know water, but bigger in that it has a larger effect. It's much more than the atmosphere. Associated with these greenhouse gases, people are attributing temperature rise and climate change. So these days, we've got temperature anomaly on the order of a degree Fahrenheit, which is thought is going to get to be bigger and bigger and bigger as the years go on. Given how cold it is in the winter, it's not clear that this is a bad thing.
I was just reported, I think over the weekend, I think last week, that 2014 is the hottest year on record.
Yeah, that's right. So if you could take this observation, work on it, and turn it into technology, a source of clean nuclear energy, and have an alternative to various fossil fuels, non-renewable resources. There's no greenhouse gas. As we'll discuss, helium-4 is seen in amounts commensurate with the energy. And helium-4, if it's released in the atmosphere, goes to the top of the atmosphere and evaporates away. You get too much around locally and you breathe it in. You can sound a little bit like Mickey Mouse. There's lots of deuterium available. None of deuterium in the ocean is at a level that, actually, you have to help me with this, I don't remember, but it's something in the general order of 1 gallon worth of the energy of 1 gallon of seawater due to deuterium is on the general order of like 1,000 gallons of gasoline. I have that on your slides. I have it on the slide, I just can't remember the number everywhere. Compared to 6,000, yeah, it's about 1,000. There's a good energy to weight ratio, which means a big impact on robotics right now. I mean, robots being mobile is tough because they have to carry their power supplies around. The energy per unit mass for chemical power supplies is not very attractive. And what you can do in like space travel changes qualitatively.
If there may be a lot of deuterium available, but there's not a lot of platinum and palladium available, so those seem to be more limiting factors than deuterium.
I agree strongly with that. However, what we're going to see is that what we're going to see before the course is over, we're not going to see it today, is that nickel is the kid sister of palladium with respect to this. Nickel's quite a bit cheaper. And if you're doing electrochemistry, you'd like to have platinum, because platinum doesn't get attacked in your electrochemistry. But if you aren't doing electrochemistry, then platinum's not going to be required either. In fact, Mitchell will talk about a technology that is free of both platinum and ultimately palladium. That's coming later. In 1989, DI got started to, they were tasked to look into the area. They got the ERAB committee to do a study in the area. DOE ERAB committee is no friend of cold fusion. About as negative as you can get. However, you can find in their report statement a simple way to harness this energy would be extremely important discovery. So even the skeptics and critics are united in suggesting that if this is real, it's important. John Huizenga, in his impartial story of cold fusion, the fiasco of the century, you can find him writing about the energy of the energy's field. True, it would be an extraordinary accomplishment. So you have everyone across the board in agreement here that clean nuclear energy source of the kind being talked about as an interpretation of the Fleischer-Pons experiment would be important, be a very significant advancement. So, takeaway message. Well, takeaway message is this: that ecstasy in the Fleischmann-Pons experiment has a potential basically to turn our society basically upside down. Have one of the biggest impacts on society there's been probably since the invention of fire. Let me pause. Comments, thoughts, or questions? Okay, so if we're going to believe it, we're going to need reasons to believe it. We need, if Fleischmann and Pons say that they can do this, that's a nice thing. But in science, if somebody pops up and says, I think this is true, you say you bookmark that, and then you wait for somebody else to say it's true, and then you wait for somebody else to say it's true. You need confirmation of science before you believe anything new. And if it's big, if it's new and it's big, then you'd like to have as many confirmations as possible. So, Dick Garland, who is a very important player in this business, we have him quoted that basically he bets against a confirmation. Laboratories all over the planet fired up. So the announcement was March 23rd, 1989. By late in the day, March 23rd, 1989, laboratories all over the world were collecting heavy water and palladium, going into the lab and start doing a set of experiments. So it was done at Caltech. Nate Lewis and collaborators. So here's the palladium, here's the platinum. Basically, they didn't see anything. The accuracy of their measurements were within 5 or 6%. And they got power balance to within the accuracy of the calorimetry in all cases. An experiment was done at Harwell, and this one was particularly important because the Harwell team was being assisted by Martin Fleischmann. Fleischmann got them, visited them, coached them on what they needed to do. Here's their cell. It looks something like the Fleischmann-Pons cell. And as it turns out, here's the results. Here's excess power in percent. So the accuracy of their system at 2 sigma level is 15%, and they're bubbling up and down. And they don't get signals large enough to be deemed a positive result. So,
I had a question on that. That is using their sliding average from 0. When you take the average of time and move it along, we get 4 bursts. I don't see the 4 bursts. And averaging it from t equals 0 over 60,000 minutes.
yeah, their data was analyzed. Harwell, in response to requests by Yes and Neelich, spent some time looking over the data, and they concluded there were positive access increases in the data.
And only in the D2O
right.
system.
However, in the initial Harwell paper, they reported a negative result. And of course, people won't go back and look to see what really happened.
If you flip back one slide, just for a minute, so I can get the rest of the reference. Thank you.
Bell Labs, those of you who have got gray hair remember a time when Bell Labs was the premier applied physics lab in the country, if not the world. Bell Labs is a victim of a change in the tax code. Anyway, Bell Labs took up the cause, and they did a set of experiments. And here's 20 milliwatts, again, a signal around 20 milliwatts, which was deemed to be too small to be positive result in their experiment. Namely, I'm using words saying, it's a little bit above and deemed to be, but I don't think any of these, except for the Harwell experiment, I'm of the opinion that this saw nothing, the Caltech experiment saw nothing. An experiment was done at MIT, and this is a big effort, attract a lot of attention. made a lot of noise, is referenced by the Patent Office, U.S. Patent Office, even these days, as providing proof that there is no excess heat in cold fusion. And here is the result. This result is much better than all the rest of them. The total energy that you can glean from this data is 0.000. There is no excess energy here, and that's in part because the MIT team calibrated their calorimeter in this case based on the assumption that there was no energy produced. So this proves that there was no energy produced at MIT. Over 100 confirmation experiments were reported in many labs, giving no excess heat. Dieter Brits, molecular chemist in Denmark, has a bibliography he's compiled with close to 1,500 papers in it from the mainstream published literature and other sources, and he's documented in great detail the story. Dieter Brits is no fan of cold fusion. He'll become important a little bit later on today. The takeaway message, important. So the Fleisch-Pann's claim of excess power is stunning. It's important. It has implications that are enormous. However, a report of such a massive claim from one laboratory isn't going to be enough to carry the day by any stretch of the imagination. And in the early days of 1989, 1990, the great majority of laboratories doing experiments in the area saw nothing. And because of this very large absence of, or large presence of negative results, the skeptics generally looked at that and said, look, this isn't real. It's not reproducible. Any pause for my thoughts or comments?
I found a really apropos article in the medical literature about this situation by Altman and Bland called "The Absence of Evidence is Not Evidence of Absence."
But in this particular case, for us to believe in excess heat and Fleisch-Pann experiment, we're going to want to see a presence of evidence. And having an absence of evidence isn't anywhere good enough.
Did I understand you were describing the MIT experiment? They calibrated perhaps not using, say, non-deuterated water, just using light water?
No, they did an experiment with light water, and the light water showed no excess heat with a normal kind of calibration. In the case of the heavy water, because the heavy water experiment was so special and so important, the MIT team was focused on seeing a burst event. If you remember the Fleisch-Pann's data showed nothing, burst, nothing. So MIT, the original data seemed to have a little bit of a positive offset, which wouldn't be good in a publication from MIT on this problem. So I don't actually know what the reasons were. I have no insight into the inner workings of the MIT team. But between Gene Allen, Mitchell, and others who pursued this, they eventually found that the data that was published had been calibrated in such a way that the total energy was taken to be zero, so they would calibrate the data.
That doesn't make the statistics, but it's like live and die by calibration. It's kind of a central function of any scientific aspects.
At MIT moved science forward.
For the clarification.
To quote Chairman Mao, the key to success is politically correct thinking, or something. Your questions are a great question. I don't have an answer. I cannot defend what this particular group did. I think it's outrageous myself. But what is this? Okay. I want to take this one step further. Back in the 1990s, Douglas Morrison used to stand up and show plots of negative publications as a function of time, and use that as an argument to show why cold fusion is pathological science. And you know, I thought it was silly at the time, but it was ridiculously effective. And for whatever reason, I was motivated to go back and look at these papers. So Dieter Britz actually helps us greatly because he's got this website where he's got a compilation of references of all of these publications. And he's a particularly good job on the negative results. He doesn't do anywhere near as good job on positive results. He's less interested in papers and positive results.
He doesn't review papers from conferences, okay? The majority of our work is at our international conferences, and he won't include them.
He only includes
The
refereed
negatives.
published journal articles. Now, as it turns out, we happen to have a journal these days with refereed published journal articles. And he
Once
doesn't
Smiley went down,
of the journal Condensed Matter Nuclear Science. And
it's you.
that doesn't
He doesn't do that one either.
that one's not next
So
to mine.
why?
Well, as you'll see, this is very valuable. I found this incredibly instructive, this exercise. So I can download the database and can write some programs to search the database automatically and call through the papers and then search through much more carefully and individually the data. And here they are. This is the proof of published papers in mainstream journal database bibliography. So 1989, 1990, this is 50 some odd, 60 some odd papers. There's 217 in all. You can see most of the papers were early. A little bit later on, once cold fusion had been dispensed with, there was no reason for publication anymore.
Beating a dead horse.
Exactly. But this is actually serious. Back in 1989, 1990, I sat down with an MIT physics professor. I wanted to talk to him about cold fusion. And we were trying to set up to do some experiments. He said, well, the thing you've got to do is if you get a negative result, you have to publish it. You got to get a positive result, you don't publish it. And if you're going to think it's true, you got to look at all these papers. You got to stare at every single one of them and explain why they made a mistake. So 217 papers, sit down, it's a lot of work. It's like Hercules in the stables, cleaning out the stables and so forth. So much work was done, lots of negative results. 217 papers in the Britz bibliography. Now, unless you're prepared to go through and explain to your scientific colleagues what's wrong with research in every single one of those papers, they have no reason to listen to you. So later on today, we're actually going to come back to this person.
I just wanted to mention that if I recall, Mike Mielich and a colleague did applied Bayes theorem, analytics to the body of work, and came out with a result that I thought, I don't remember exactly what the result is, but indicated that there was a there from that exercise.
Well, we'll have some much better exercises than
Welcome back.
that. All right. Okay, I'll talk next about molecular P2 fusion. So the argument is, back in 1989, people were trying to understand the problem of fusion. So if you load deuterium into palladium and you're thinking that they're going to fuse, what's a reference physics problem you can stare at in order to get some intuition understanding about it? And D2 fusion was the reference problem that's chosen. Many physicists focus on the analysis of D2 fusion, screened as it might be in palladium and otherwise. So the problem is deuterons have charge, so the Coulomb interaction pushes them apart. Because it pushes them apart, there's a barrier, you can push them together, you can throw them at one another pretty fast in order to get them to come together. So here's the fusion cross-section. What's a cross-section? Cross-section is an area. I guess the simplest way to do it is to imagine a pitcher throwing the ball towards the plate in a baseball game. And there's a little window where you got a strike occurred. The window you can think of as having an area. So the area is defined in that case for the picture is the cross section for getting a strike being called. Isn't that it doesn't so if it's outside that area, it's not a strike. If it's inside the area, it's a strike. So in the same way, if you got one deuteron coming in, actually two deuterons coming towards each other, you can imagine one presenting an area relative to the other. And the area here is 10 to the minus 24th centimeters squared. 10 to the minus 24th centimeters squared is a very small area. The nuclear physicists of the bygone day thought, oh, can't hit the broadside of a barn, so this is a barn. So anyway, we can see that if the relative energy between the reactants, deuterons in this case and DT in this case, is below 10 keV, there's basically very little probability of having a fusion reaction. In the case of DD fusion, you get a cross-section that hasn't even maximized when the relative energy is an MeV. So as a result, to get fusion, DD fusion to work, at least by the way we understand nuclear physics, you need high temperature. For example, in the sun or in a magnetic fusion device. So people put in an awful lot of time, money, effort, sweat, building experiments that reach very high temperatures in order to be able to get deuterium to fuse. Because of this, the notion that an electrochemist can go in the lab, hook up a couple electrodes, pour in some heavy water, run an experiment for some number of days, and make fusion happen is reality found. It's ludicrous. It's ridiculous. I mean, if it could be done so easily, then people would not be spending billions and billions of dollars building these devices. They'd be working on cold fusion. But they're obviously not working on cold fusion, so the scientific community knows that cold fusion isn't real.
The marketplace has spoken.
Okay, so the question is, how do you get the deuterons together? If you don't have the temperature, then tunneling is the only other way. So in quantum mechanics, most of you may be familiar with the notion that you have a particle incident on a barrier. Classically, it bounces back. Quantum mechanically, you have a small probability. You have a probability, which can be small, of tunneling through the barrier. In the case of the molecular D2, and this is why it's important analog for this problem, you got two deuterons. You've got a potential barrier. This is the potential. This is the distance between the two nuclei. So this is in units of Bohr radii, which is 0.529 angstroms. So somewhere around here is 1 angstrom. As the two deuterons get closer and closer together, you've got potential that's getting larger and larger and larger. So you have to try to tunnel through this potential. So it's basically a straightforward calculation to do the tunneling calculation. So in this case, I've calculated the radial wave function for the D2, for molecular D2. And what I see is that most of the probability is centered around the equilibrium distance of the two deuterons, 0.74 angstroms. As you get the two deuterons to be closer and closer together, so you have to be around here in order for there to be fusion. The wave functions down here at something in the general neighborhood of 40 orders of magnitude down from where it was here. And that being 40 orders of magnitude down basically means you've got a very small probability for tunneling. So Kunin and Allenberg and quite a few other authors went ahead and did calculations of this sort. Theirs was more accurate than mine. And for the case of DD fusion, they get minus 63.5. What that means is the rate at which reactions happen is 10 to the minus 63.5 inverse seconds. So all you have to do, if you're patient, willing to wait 10 to the 63.5 seconds, your D2 molecule in this model will fuse. So what I'm going to do is think a little bit about the calculation. I want to think about it in terms of a intuitive terms. So here's the rate for fusion, which is the 3 times 10 to the minus 64 inverse seconds, very slow rate. So I can take this rate and I can split it into 3 factors. One's a tunneling factor to tunnel through the barrier. Another is a volume factor. You're starting out with a big molecular D2 molecule. You're ending up with a very tiny helium-4 nucleus, or 3 plus 1 proton plus a triton, or neutron plus helium-3. And this is the reaction time of, if you manage to get the 2 deuterons close to within a nuclear volume, how long does it take for them to react? And that's a very short time. So the overall reaction rate is the time they take to react once they get together, times factors which tell you the likelihood of them being together. And a telling factor, which is about 3 times 10 to the minus 70th from Kuhn-Youngberg type calculation and my calculation. The relative volume of the molecule and nucleus, it's basically 10 to the minus 15th. It's angstroms to Fermis. And then if you use these numbers, then the time associated with fusion of 2 deuterons so localized is about 10 to the minus 21st seconds. Namely, very hard to get them together. Once they get together, they react very quickly and they go flying off. The thing to add into this is that the nuclear interaction, which mediates the reaction, is of short range. Like on the order of Fermi. So being of such short range, you really do have to have the deuterons being very close together in order for them to react and fuse. Now, this argument's extremely powerful because what it says is that once they get close enough to interact, things happen very fast. This is so fast that your speed of light limited talking to anybody else. Namely, if you've got another, if you want to come up with some kind of theory or model that says your fusion reaction is going to be interfered with by other atoms or other electrons, then you can say, well, okay, if it's going to interfere with the fusion, you've got to be within a speed of light distance to be able to communicate. The speed of light distance is 3 times 10 to the minus 11, which isn't very far. 3 times 10 to the minus 11, the nearest is a couple of angstroms away, which is a couple of times 10 to the minus 8. So you're about 1,000 times too short speed of light distance in order to actually reach the next atom. So this argument was used back in 1989 to basically eliminate all possibly theoretical mechanisms. You're going to say DD fusion happens in some fancy new way and you're invoking the physics. Or you can say the speed of light limitation based on this kind of argument means that, I'm sorry, you can't talk to anybody else because the information that the 2 deuterons have gotten close enough and are not ready to interact, that information you can't even get to the next atom in time. So people made arguments saying, well, saying that cold fusion can happen in a lattice because the interference or influence of the other atoms is a little bit like saying that you're going to do an experiment in the lab and you're worried that the moon is going to impact what's going on in your experiment in the lab. The scales are orders of magnitude difference. The primary fusion reaction channels are 3 plus 1. Deuterons have got a neutron and a proton, so it's got 2 nucleons. So 2 plus 2 goes to 1 plus 3, 1 plus 3. So half the time, roughly, you get a neutron, half the time you get a proton. The cross-section's been measured. So it turns out you get a ratio close to 1 that's a little bit on the other side. A little bit on the other side, when the 2 deuterons get close together, turns out the proton likes to be further away because of the Coulomb repulsion. So you get a little bit of favoring one reaction over the other. It's called Oppenheim-Phillips. The takeaway message is basically the molecular D2 problem was used to be analog historically, and even today, if you were to wander down the hall and ask folks in the physics department, they might reference you to this problem. You understand that there's a big barrier. You don't have the energy to make it through kinetically. You've got to tunnel through it. Tunneling through is hard because the barrier is really very, very large. And then once you tunnel through it, things happen very quickly. You don't have time for anything else to happen. And in a sense, that rules out all hope. If you were a believer, if you had been a believer and thought that some of these experiments were right, and if you know some physics, this argument should be sufficient to convince you that it's completely hopeless and the experimentalists are just making mistakes. Let me pause and entertain questions, thoughts or comments or questions. So I've convinced you.
I had read as a layman when Fleischmann Franz first came out that there had been historical analogs to what they did. For instance, there was an experiment in the 20s which saw something like that and they could explain it. I was wondering if historical references to what Fleischmann did.
Yeah, back in 1989, 1990, people were very interested in all historical stuff. So it's the experiment you're referring to is one by Panic and Peters, and basically did experiments early on. They thought they saw some helium. They couldn't understand it. People understood at that point that it didn't seem to be consistent with what you would expect. They went back and studied how helium diffused through various things. And as a result, and in part as a result of that exercise, people actually figured out how to make helium link type equipment a little bit better. We'll talk a little bit about helium diffusion and so forth. I don't actually know what to make of it. I've read these things as well. Some people claim that there's been anomalous effects seen much earlier than Fleischmann-Pons. There's other folks saying, well, you don't know. And you don't have the paper saying, well, here's the experiment, here's the energy, here's the helium, here's the application, and so forth and so forth. People don't allow to see things, they don't understand it. You don't know what to do with it. I certainly don't know what to do with that.
I think Seaborg put it very elegantly on the relationship between the chemists and the physicists that you alluded to a few minutes ago in his 1995 talk at Liverpool's out there. I think Griffith put it up on YouTube. And he said that the chemists had thought they had stolen the march on the physicists.
Yeah, I think physicists don't take kindly to chemists doing nuclear physics. Okay, let's talk now a little bit about theory, sort of a little bit more generally. So we've seen that Fleischmann-Pons claimed excess heat. We've seen what a gigantic claim it is. We've seen a little bit how what a big difference it would make. We've seen now 217 papers showing negative results and efforts to replicate it. So we have an absence of confirmation. We have the molecular D2 argument as to why it's impossible theoretically. But I want to take it a step further and think about theory more generally.
Remember now the question I was going to ask about the 217 reports that all have to be reviewed and showed why. Seems to me that kind of goes against the spirit of the scientific endeavor, because where does the burden of proof lie?
Actually, for whatever it's worth, before we're done here, we'll think about all these references.
Good, thank you.
I mean, folks working on cold fusion have clearly been given the burden to prove everything with no resources. Let me divide up the world, divide up the relevant theoretical world into a nuclear physics arena and condensed matter physics arena. Because of the separation of the degrees of freedom associated with nuclear physics and condensed matter physics, the two disciplines separate naturally. So big bar between the disciplines. So we go to the library, there'll be nuclear physics journals, there'll be solid state journals. There's not very many journals that say solid state and nuclear physics. Although the Condensed Matter Nuclear Science Journal is one such, and then shortly after that was founded, there was a physics journal, which is Condensed Matter Nuclear Physics in accelerated physics or synchrotron radiation. So there are some journals now that deal with both. But in condensed matter, you've got a story back in 1989. It was a very successful story. It's more successful now. In nuclear physics, you've got you've got a quantum description, you've got nuclear potentials, you can calculate things, and it's very successful. So you've got an accepted theory for how condensed matter physics, you've got an accepted theory for how nuclear physics works. You've even got some more fundamental field theories which provide a foundation for all of this work. And you can separate them cleanly and clearly. Let's think a little bit about palladium deuteride. Palladium deuteride is an FCC structure, face-centered qubit. So think of it a little bit as checkerboards. So palladium's on the black spaces in this plane, the deuterium's on the red spaces. The next plane, black spaces and red spaces, except shifted over a little bit. And then this one's the same as this one. So you've got the deuterium sitting in octahedral sites, you've got the palladium atom sitting in the original FCC lattice. And in a sense, you know, if you're a solid state physicist and you're looking at it, you say, this is a very simple structure. You know, there are no mysteries with respect to palladium deuteride from a solid state perspective. Now, if you have a solid, you've got vibrations, and at this point in palladium deuteride, we used neutron scattering to figure out the vibrational degrees of freedom. So how vibrations occur is understood from measurements. At this point, there's been 3 measurements done over the years of the photon dispersion curves with neutron scattering, and these can be compared against models that people make up for these things, and the agreement is very good. For our next plot, we're going to need to understand something about the directions and labels. So you've got an X, Y, and a Z direction. If you go in the basically 1, 0, 0 direction, you get an X point. If you go in the 1, 1, 1 direction, you get an L point, and so forth. But here are the electron bands, and the different directions are on the axis down here. So palladium, you can calculate the electron band structure. If you add hydrogen, if you look at it, you get in many cases quite a complicated band structure. Some features shift a little bit, the Fermi level changes a little bit. You get some extra orbitals thrown in by the presence of hydrogen. But in a sense, the band structure for palladium deuteride was worked out a long time ago. People do a little bit more accurate calculations these days. There's no particular mystery for how the electronic structure works. I was actually impressed when I was a student, we were taught band structure. The thing that I didn't see was any experimental reason why I should believe in electron band structure. And then around 1979, people started doing angularly resolved electron spectroscopy measurements. When the photon electron comes out, you can actually start to investigate the band structure directly. And so here's some experimental results for some band structure in the case of aluminum against some theoretical calculations that have been done. And what they found, interestingly and surprisingly, amazingly enough, is that the electron band picture is basically largely okay. Some shifts in the bands, you need a more complicated theory. You need a field GW theory people use to understand it these days. But anyway, it works. So largely, well, we can understand things. We've got to figure out how the bonding works in palladium. You know, the deuterium goes in octahedral sites. You know that from neutron scattering experiments, you know, theoretically and experimentally. Octahedral sites, which we'll be talking about with the higher electron density, hydrogen doesn't go there. You can't fit H2 or D2 into an octahedral site. Not that it's too big, but the electron density is too high. There's nothing obvious that's special about the palladium deuteride structure that would make it different from anything else. I mean, if you were looking for something that would maximize deuterium fusion in solid state, probably what you'd like to do is look at deuterium metal. So if you compress deuterium to 100 gigapascals or a couple hundred gigapascals, you can crush it down into metal so the deuterium is pretty close together. You get electrons around for screening. That would be the kind of thing you'd be looking at if you want to get into the fusion. But palladium deuteride doesn't do anything remotely like that. It's not a particularly interesting candidate. In the case of nuclear physics basically started out along with the other kinds of physics following the advent of quantum mechanics. Actually, experimental nuclear physics started earlier, simple pictures and stuff. But in the 1940s and 50s, people made an effort to try to derive nuclear physics from notions of pion exchange. And these earlier models were not particularly successful because the nuclear potentials that we derived weren't very good. In the late 1950s, people said, well, instead of trying to derive from scratch, why don't we measure it? Let's measure the proton-proton scattering, neutron-proton scattering. Neutron-neutron scattering is a little bit harder to get at. But the scattering was measured, and they said, well, let's put together an empirical potential that matches the scattering data. And that was done. And as soon as that was done, nuclear physics took the quantum leap forward. It started to become quantitative. You could start doing nuclear physics calculations from scratch, ab initio type calculations to get good answers. So for example, this is a 1985 paper. Look at triton. So triton's 1 proton and 2 neutrons. It's a 3-body problem. So the experimental binding energy is 8.48 MeV. So here's for each soft-core potential, and there's an argon-14 potential, 7.67 MeV, 7.35 MeV. You can say, well, it's not precise. You would like to get it to 10 digits or so. Well, it's not where nuclear physics was in 1985. The issue, again, has to do with the potential. Recently, Stephen Weinberg proposed an idea of effective chiral field theory to describe the nuclear force. And this has been worked out and fit and put together. So here's a 2009 paper. Here's experiment 8.482. So here's the calculation now with this new super duper fancy chiral effective field theory 8.474. You can see that this is very good. So the basic idea is that in nuclear physics, you've got a quantum mechanical framework. Two-body problems can be worked accurately. In the case of DD fusion, years ago, here's the 1982 calculation. You've got basically you've got comparison between theory and experiment. And as you can see, the cross sections, the cross section which we saw goes down, goes back up. It's got various factors. If you take out the exponential factor, energy factor, you get something slowly varying left. And this is the calculation slowly varying part using the nuclear physics, using the potentials of the time. And I don't recall which potentials these are using. I'm assuming that this one's probably argon potential. But these things have been redone now with the new chiral effective field theory potentials. And the agreement is superb. So the basic idea is that in nuclear physics, the deuteron-deuteron problem is an easy problem. It's been studied for years. It's known exceedingly well. The fusion reaction mechanisms are ridiculously well understood at this point. We've been calculated to precision. The excited state spectrum of the 4-body problems we calculated has been understood for decades. There's no mysteries. There are excited states. They're highly unstable. They've been studied theoretically and experimentally. So you stare at nuclear physics and you say, well, this thing that Fleisch and Pons is talking about to get energy in some new way from the DD fusion process, it's just, it's ruled out completely. It's not something that's on the borderline. Well, if this were true or if that were true, then it could, it might work. It's just that there's no scenario in these models was understood in 1989 or today within the mainstream physics community, that anything even qualitatively remotely like this could possibly occur. So takeaway message, dense matter physics, nuclear physics, they're mature fields. Plain deuteride is simple. Deuteron fusion is simple. Basically everything that you could want to know about these things is available from experimental work and theoretical work. The guts are understood theoretically. There's just nothing in these problems at all that would lead one to believe that you could get anything remotely like what Fleisch and Franz are talking about to happen. Let me take away a message. Let me pause and catch my breath and entertain questions. Or thoughts. No problem.
I guess I'm almost surprised, given all this, that there were 217 papers written. That seems like a pretty serious effort. Given it's clearly impossible to make physics as heat, there cannot be an anomalous fact in there. Even though that seems like the basis of all physics.
Fleischmann, prior to this announcement, had a good reputation. He had won the palladium medal of the Faraday Society. He was basically one of the experimentalists who knew more about palladium hydride system, palladium deuteride system, than almost anybody else. Now, electrochemists have capability to do calorimetry pretty well. And so for Fleischmann to pop up and say, I'm seeing more energy out of this system than should be there, that had to be taken reasonably seriously. And once it was, once the announcement was made, because it's such a big deal, namely, basically somebody popping up and saying, well, I have a unicorn at my front lawn, would you like to come over and take pictures of it? So as a result, because of the significance of it, because of the presence of very large, well-funded fusion programs, this was a topic of interest basically to everybody. And a lot of people were motivated to go in the lab and do something.
Is there any evidence that Fleischmann knew about this at the time when he was wading into in terms of this context of extensive theory development in the 1989 timeframe? Or follow-on question, did he become aware of it afterward and comment about that?
I'm completely sure that Fleischmann didn't understand about the intricacies of nuclear physics and didn't understand about the intricacies of solid-state physics. He wasn't surprised at the negative response. He was expecting that. I think he told me when I talked to him that he was expecting it, but he wasn't expecting at all the magnitude of the antagonism of the response. From his point of view, he thought, well, there'll be like a normal field that a lot of people will compete. Some people will understand what's going on, get positive results, some people won't. And you know, he's a very competitive kind of guy. And he never foresaw the manual science study. That wasn't part of what his vision was.
Two asides. What you said about the unicorn was the James Thurman story of the unicorn in the garden. And when you were talking about the 217 papers, it's like the old economist joke. The economist sees a $20 bill on the sidewalk and says, that can't be there because if it was there, somebody would have picked it up.
Yeah. Well, so I'm thinking, what am I thinking? So I'm thinking, if cold fusion is real, I'm just looking at this sideways, if cold fusion is real as an experimental reality, then it would imply that there's something very fundamental about condensed matter physics that we don't understand, and perhaps as well something very fundamental about nuclear physics that we don't understand. And in a place like MIT its people understand nuclear physics very well, understand condensed matter physics very well. If you go and you knock on your door and say, well, sorry guys, you screwed it up. You can imagine, of course, be thrown out the window. It's like defenestration from medieval days. Skepticism. Probably it's clear at this point that there's some room for skepticism. So the announcement was March 23rd, 1989. There was a time where it was in the magazines and the newspapers and TV and radio discussion. It was a very big deal. By the beginning of May, it was knocked off the radar screen completely. Some early cartoons. Heisenga wrote a book describing the various things that happen. Also, Gary Taubes wrote a book. Other folks wrote books. Frank Close wrote a book as well. Heisenga, in his book, described 3 miracles. And then actually 3 miracles have been discussed before that. But Heisenga's 3 miracles are 1. This is primarily the headache from a nuclear point of view. How do you overcome the Coulomb barrier? So for example, today you can find some theorists saying, well, the deuterons don't see the Coulomb barrier. Everybody scratches their head and looks at them and say, but why should it vanish? So Coulomb barriers can't vanish. And as a result, if you're at room temperature, you've got to tunnel through it. And tunneling through it, as we've seen, is a very tough thing to do. You got a branching ratio miracle. Suppose you magically somehow manage to tunnel through the barrier, the 2 deuterons get close enough together to do something, then we would expect them to come out as 3+1 reaction, neutrons and protons and so forth. Clearly, the neutrons and protons aren't there. The neutrons you would be able to see from neutron detectors outside easily. The protons were there, you'd be able to see them also, but that's a little bit more subtle issue. So the question is, if Fleischmann conjectured, or people conjectured in 1989, that maybe helium was made as a product. So the question is, how in the world do you get helium to be the preferred reaction pathway? So in nuclear physics, there's very good reasons, very obvious reasons. In fact, the reasons are called conservation of energy and conservation of momentum, which is why these guys come out. So on a microscopic scale, if you want somebody else to come out, you're going to have a very good reason as to why they come out and not this. You have to suppress neutron emission and proton formation somewhat. And by what was known in 1989, as well as what's known in nuclear physics today, that's just impossible. It's outrageous. It's ridiculous. Finally, you've got the concealed product miracle, which Heisenga argued that you're going to get helium-4 to come out. And in nuclear physics, both theoretically and experimentally, it's understood that DD fusion can give you a gamma coming out. So if you can get helium for each juice, you better have a gamma. And gamma's not there. It's not clear. Now from my, I don't think Heisenga went anywhere far enough on this third concealed product miracle. He was focusing on helium-4 and gamma. But as a much more general statement, so here's my expansion of Heisenga's third miracle problem. Where's any commensurate nuclear radiation? Now, I don't require just a gamma. Show me anything commensurate. If it's going to work, there's going to be a nuclear reaction. And if you believe that nuclear reactions have to give their energy through nuclear radiation, show me commensurate energetic nuclear radiation. Not only would you have to hide your gammas, you have to hide neutrons, protons, alphas, electrons, neutrinos. And neutrinos, of course, are hard to detect, so that you presume can hide, but then you wouldn't get your energy density. So skepticism. Steve Kernan, who recently was Undersecretary of Energy at the Department of Energy, argued that basically excess heat leotard is the result of incompetence and delusion of Fleischmann pawns. The audience sat in stunned silence for a moment before bursting into applause. yes, science strikes back. The infidels are hammered down into rubble. Sir John Maddox, who at the time was editor of Nature and who had training as a theoretical physicist, he called fusion as discreditable to the scientific community as a whole. Licensed magic, could be unicorn snacks, claims equal credence even when they fly in the face of expectation by exertation. Physically means theoretical physics here. From the frailty of collective confidence in theoretical science, why should so many people be bamboozled for so long? These are very, very strong statements. And oftentimes, people think of scientists as being calm, impartially do their science. You don't get to see fire breathing very often in scientific community. I note that I was looking at Sir John Maddox on Wikipedia to try to learn more about it. And found it. He also didn't buy into the Big Bang when the Big Bang theory was announced. So the basic situation is that Gaussian ponds claimed excess heat in their electrochemical cell. It goes against theory, it goes against solid state theory, it goes against nuclear physics, doesn't stand up to the weight of experimentation. It's been tried in the various fields. We've got court of law, we've got orators, we've got God himself working at the electrochemical cell. The soul of cold fusion has been judged and weighed against a feather and found wanting, summarily dismissed. So at MIT, a wake was held and was scheduled for June 26, 1989, so March, April, May, June. So this is 3 months after the initial announcement. And cold fusion was put inside the community. Thank you for your attention. Any questions? Yeah.
If I remember correctly, April 26th, was it April 26th, 1989, was Chernobyl.
I don't remember the dates.
But, I think that's within the time stream, that's a little interesting to see that as well.
So takeaway message. So the biggest issue, and this is the issue we're going to be wrestling with through the end of this course. Okay, the course isn't quite over. There's 1 or 2 more issues left to chew on. So excess heat's not consistent with accepted theory. And I cannot overemphasize how important this is. In fact, by the time we're done, we're going to have to wrestle with this, and we're going to have to face up to it in all of its glory. But in the meantime, you've got theoretical reasons why it's impossible. You've got lack of confirmation. The implications of the experiment must be wrong in order to make things self-consistently. Fleischmann, Pons, other people in the field were attacked and discredited. In fact, all experiments theories, scientists, people who call themselves, people who beforehand might have been accepted as scientists were no longer considered to be scientists within the scientific community for persisting, believing that there might be anything to all of this. So takeaway message, questions, comments?
It's too bad that burning at the stake is out of fashion these days.
Believe that they'd be willing to bring it back in this case, make exception. Yeah.
Anomalous facts usually the way we find the next theory. Is that how?
In the old days, the idea was you did an experiment, the experiment's not agreement with your models, so you just fix your models. But implicit in this, I didn't emphasize it enough. Things are different these days. The physics as an enterprise, has succeeded beyond its wildest dreams. For example, with the advent of quantum electrodynamics as a theory around 1950, the situation sort of changed qualitatively. QED is sort of the most successful theory in science, having been around now for 65 years or thereabouts. During the 65 years, there's basically been no experiment, no observation that seems to be significantly at variance with QED. And that was up to some recent measurements of quantum shifting, ionic quantum shifting in the atmosphere. There's a little bit of disagreement, which has people in physics really running around in circles and doing calculations and scratching their heads. But aside from that, QED is understood as being the answer. Namely, there are no more laws of physics in that area, fundamental laws of physics to be had. That's how it works. And then the generalization of that to QCD around 1964 or so provided basically a similar level of basic theory to describe nuclei. Continuing on, it was augmented to give us the standard model, including electroweak interactions. So for everything except for gravity, there's a fundamental theory now, which is basically understood as being correct, at least correct for all practical purposes. So if there's ever a question of an experiment, we've got something we can reference it again to prove whether it's right or wrong. So some of the skeptics back in 1989, in order to raise a red flag in front of the theoretical physics community, suggested that the standard model is inconsistent with flesh and pods. And certainly the scientific community understands that to be true these days. I don't believe it's true, but that's where it is. So the answer is in times past, you start with experiment, you got a theory. These days, to be honest, certainly in this field, it's different. These days, you start with theory. The experiment happens not to agree with theory. I'm sorry, the experimentalists are the ones that are wrong. It's a pretty sad state of affairs.
So, Peter, presumably in 1988, 89, you're minding your own business. What got you beyond idle curiosity? I'll ask you this.
I had previously been involved in multidisciplinary research. For example, I got involved in the field of X-ray lasers long before there was X-ray lasers, and at a time where people would sit down and explain to me that I was wasting my time because there would never be an X-ray laser, certainly in my lifetime. And well, X-ray lasers came to pass, and so forth and so forth. At the time of the announcement, I was sort of young, new on tenure faculty at MIT, and I missed the announcement because I was traveling, was in the air, and I ended up in Livermore the next day, and visiting with my group, and my group explained to me that if I wanted to get paid for my consulting trip, I had to figure out how cold fusion worked. I didn't succeed during that trip in figuring out how cold fusion worked, but their judgment was that this is a multidisciplinary problem, that likely it wouldn't be taken seriously. Somebody needed to be thinking about it and figuring out how it worked. When I came back to MIT and visited some of my colleagues at MIT, said, look, this problem's got your name written all over it. It's a multidisciplinary problem, it's a tough problem, and it's one that isn't going to be solved simply, easily, and quickly. So I took an interest in it. I mean, my own perspective, in spite of my encouragement from my colleagues, was that if all you need to do is a derivative electrochemistry to make nuclear physics happen, this is magic that we really need to know about. That was more than enough motivation for me to work. Also, from previous years, I've been very concerned about energy, fuel, smog. I didn't know about climate change, but I was worried about us running out of fossil fuels and so
What was the third example? quantum electrodynamics and then quantum thermodynamics and then
GCD and the standard model.
standard model. Okay, thank you.
More take-home message. So if the excess heat's real, then we have a major challenge to condensed matter in physics and nuclear physics. Basically, the scientific community's other point of view. If you want us to believe in any of this, not only do you have to show us experimental results, which you're not going to take. I mean, even if you have reproducible excess heat, say at the factor of 50 or 100, turn it on, turn it off, it's just not good enough. What the scientific community demands is that, you know, if you think our nuclear physics and our condensed matter physics aren't good enough, show us new physics that works better. So the theoretical problem comes part and parcel with this problem that if you want to convince the scientific community, not only do you have to explain that it works, but you have to explain how and why it works, and you have to explain what's wrong with current accepted physics. That's the task. That's the tasks that charge them. Shall we go on? Positive results. Of course, there were a few positive results. There's actually been contributions from a large number of institutes for excess heat, and this list includes other things besides excess heat as well. For example, in an early experiment of SRI, here's the excess heat which they measured. Here's watts. A couple of watts. There's integrated energy. So in watt hours. Here's an experiment from Imra, Japan. Basically, they saw excess heat. This is Kunimatsu, so I guess this was probably a fuel cell type system. So the current density inflation ponds experiment above 100 milliamps per square centimeter, they would see excess heat at low current densities. It's nothing. Here's an early experiment from Ed Storms. So you can see some excess heat coming up. He's got a failure in his recombiner. As the excess heat continues. These are big signals. So the question is, as Shanahan says, yes, the signal's small in comparison to the noise. You can hardly see it, you can't be sure of it. If you look at stuff like this, you say, well, it looks pretty big to me. Here's the flow calorimeter at SRI. We've got a current ramp that goes up. We've got excess power. Here's 1 watt of excess power. Current goes down, excess power goes down. Here's another set of data from SRI. This is a light water experiment. This is heavy water, current ramps. The current goes up, the excess heat goes up. The heavy water case, the light water case was run at the same time, it saw the same current profile, and it sees much less of a result. Here's a early result published later on by Mitchell from Jet Energy. Mitchell spent time explaining this. So we've got control, the input power and the output power match each other. Here's the input power, here's the output power, so there's substantial gain here. Here's a result from energetics. So Irving Dardick proposed the use of super waves. And people say, what are super waves? And so super waves is this. Well, what's that all about? I said, well, have you ever had a drawer that was stuck? Right, you want to open the drawer, and the drawer won't open. So you shake it. Except you shake it in a funny way where you shake it the hardest when you're shaking it the fastest. So here, you're shaking it the hardest when you're shaking it the fastest. That's sort of the idea behind the super waves. So in one of the experiments that, actually in 4 or 5 experiments of energetics out of a great many, several hundred, very high results were seen. So in this case, 0 watts is down here. The input power was here, a little bit less than 1 watt. The output power is up here. Here's 40 watts, here's 34 watts, and so forth. So you have a very large ratio of output power to input power. In fact, in this data, the ratio is a little bit better than it was for Fleischmann Ponce 1990 paper. Let me consider the 2 laser experiments. It was found by Dennis Letts that early, it was found, do I remember when, something in general neighborhood of 2000, I guess. 2002, that if you shined one laser on a cathode that was biased just below being able to produce excess heat, with a single laser could stimulate excess heat and turn it on. And that's interesting, but the excess heat would turn off when you turn the laser on. A little bit later, Dennis tried 2 lasers. The idea suggested by me was that if you could shine in and if the excess heat responded to the frequency difference, you could probe what's going on with the different frequencies. So here's an example, no excess heat, the laser's turned on, the system responds and goes to reasonably high output power. In this case, the 2 lasers, roughly 15 milliwatts is absorbed. The thermal response is over 300 milliwatts. Note that the electrochemical power to keep this thing going at the time, input power is about 9 watts. So this is a relatively small effect, but the thing that's cool about it is that when the lasers turn on, the excess heat turned on, so it demonstrates the beginnings of control. That's why it's interesting. So here was a demo that was carried out at MIT by John Dash and his associates. So here's the excess, here's the cell, the electrochemical cell, and I got a positive result here. Of course, other cells. Mitchell did a demo also in connection with ICCF10, and we got some positive results, which we'll talk about. Anyway, takeaway message. Okay, Fleisch ponds pop up, claim this amazing result. Wasn't reproduced. Theoretically, it's impossible. And yet we have some people saying positive excess heat. By now, excess heat's been seen many hundreds of times, and seen in all kinds of different configurations, different laboratories, different kinds of calorimetry. So at this point, the basic message, and I suppose one could actually fill up 4 days easily, discussing the positive experiments, the data shown. I've been thinking that maybe one of these days I should do that instead of talking about the science and physics behind it. But the amount of data out there is enormous. We're talking about more than 1,000 papers. So this motivates us to try to understand the experiment better. And it also motivates us to say, well, you know, if reputable laboratories, if MIT and Caltech couldn't see it back in 1989, 1990, what did they do wrong? Why did we see things? So we're actually motivated to collect the pile of 217 papers, dive in and start reading them to see what the story is. So takeaway message then. Thoughts or questions or comments so far? Okay, so we recall the Wikipedia, you know, very tiny effect, 10 or 20% effect. Again, not a 10 or 20%, 10 or 20% effect. Wikipedia is badly misinformed in this case. So revisiting the negative results. So thinking, arguments against excess heat. The biggest one is inconsistency with accepted theory. Also weighing heavily on this is a large number of negative experiments. And the skeptics have decided all experiments showing positive results are not credible. You can ask what criterion they're used. And that brings to mind the KEK experience. So there's a big high energy physics lab in Japan, KEK. And they were tasked with investigating Fleisch ponds to see if they could get it to work. So they come to the conference year after year. KEK is a really competent physics lab. They got some of the best researchers in physics around. Good reputation. And they would come each time when we have a conference, they would come and they'd present the negative results. And they were wonderful people. They get up and said, I'm sorry, we tried as hard as we can. We've done everything we've loaded. We've put in the cathodes. We've done all your suggestions, but here we got nothing again. And each time they come and they say nothing, Douglas Morrison from CERN would get up and say, look, this just goes to prove when competent physicists try this experiment, they get the result you would expect. They would get nothing. And sure enough, one of the conferences they came up said, look, we saw an excess heat burst. They showed the data, and there was their excess heat burst, and everybody applauded and was happy. And Douglas Morrison got up and said, "You made a mistake. You guys are incompetent." Not a mistake away. And so the determination of credibility, I think, depends on what your answer is. If you get a negative result, you're credible, and if you get a positive result, you're not. Anyway, so I think this business of deciding credible results, not credible results, I think is well, it's an important part of science, but in this particular case, the decision's particularly silly. All results showing that are positive are deemed not to be credible. And that sweeps away all the positive results from consideration. So now, I'm going to go back. I'm going to start digging through this pile of 217 papers in order to see what's going on. And the first issue that we've got to deal with is, how do you measure for excess heat? Out of curiosity, if you guys were going to measure for excess heat, how would you do it? Would you put a thermometer in? Do some kind of temperature detection? Right. To tell if there's heat there, the temperature is going to go up. You want to measure the temperature. However, it was argued back in 1989 that if you're talking about fusion, if you're going to have DD fusion, then half of the time you're going to get a neutron coming in. You can measure that neutron very easily with a neutron detector, at least with some poor yield fraction. So as a result, people started publishing papers with upper limits on excess heat production based on neutron measurement. Now, years and years later, we went through the exercise of saying, there's been some experiments done where excess heat bursts were seen when a neutron detector was seen. So the first question, is there a correlation between an excess heat burst and neutron emission? The answer is no. And then the second question is, well, what's the upper limit? If there were a correlation, how many neutrons might you get per joule of energy produced? And from the data from experiments that have been done, the upper limit's 1 neutron per 100 joules. So, there's something like 6 experiments out there where excess heat bursts for C neutron measurements were reported with enough information so you can actually go back and figure out an upper limit for the experiment. Now, Fleischmann and Pons never argued that you were getting neutrons in connection with excess heat. So this business of using neutron detectors to measure energy, this is based on a theoretical assumption as to how the reaction works. So the theoretical assumption is that you've got a hot fusion reaction and you measure neutrons on neutron for each of the reactions. So since excess heat in the Fleischmann-Pons experiment is nearly radiation-free, I'm going to add the requirement that somebody measure temperature in order for me to accept the result as figuring out whether there's excess heat present or not. So what I want to do is I want to go through these 217 papers, and all of the papers are going to say, well, I've measured for neutrons as a way to figure out excess heat. I'm going to say, this is very good, but we know that neutrons aren't correlated with excess heat, so I'm not going to pay any attention to that result. I mean, it tells me that I don't have DD fusion with neutrons present, so it tells me that DD fusion with neutrons and protons being produced is not connected with the energy being produced, but it doesn't tell me whether there's energy being produced or not. So I start out with my 217, and probably I'm going to lose 1 or 2. And probably this neutron detection measurement for checking energy. There's not very many of them, right? Anyway, it turns out of these 217 papers, the large majority of them were actually nuclear measurements that have been interpreted as energy measurements. And so we're left with a much smaller number. Now, I've plotted it here for effect, it's smaller. 39 negative results is still more than enough to be a headache. But so we still got to go and take these 39 papers and read them very carefully. I note that Dieter Britz has very strict requirements in his bibliography about which papers he includes. And of these 39 papers, a couple of them are Chinese, some are Japanese. One's from a Korean, obscure Korean journal that was very hard to track down, and so forth. Okay. Now, so the question is, in 1989, 1990, also in connection with the DOE ERAB report, Heisenga and others, they would say, well, look, we have all these negative results, and there's no credible positive results. On the other hand, we've got Dieter Britz, who's admittedly biased. He tends not to include the positive results, but he has one or two included anyway. So I thought, just for kicks, let's try exactly the same filter on Dieter Britz's database to see what we get for positive experiments. So here's the 39 negative. I wanted sort of on the equivalent graph to plot the positives to see one or two here. There's more positive result papers in Dieter Britz's bibliography than are negative under this particular filter. That you have to be working with palladium and you have to be doing calorimetry. I found that interesting. And we're actually not done with Dieter Britz's bibliography. But takeaway message, Dieter Britz is no advocate. He's not a fan of cold fusion. There's a modest number now of negative results when you filter for palladium electrochemistry and calorimetry, larger number of positive results. If Dieter Britz's bibliography were expanded to include publications in our field, for example, this number wouldn't be 49, but it would be over 1,000. Let me pause. Comments, questions we've got so far? Nobody's impressed by this. Oh, yes. Conclusions so far. Any honest assessment of literature will show basically will show that the arguments, the clarity of this experimental situation is not so obvious, as was made by the skeptics early on. There's a minority of the papers, the negative papers, experimental papers, actually even bothered to do calorimetry. So we conclude at this point that the skeptics overstated their position in 1989 and continue to overstate their position. The biggest result for lack of acceptance of the experimental results showing XOC, in fact, is the inconsistency of theory. Comments, questions? Yeah.
Have you presented this analysis?
Presenting it.
Now, to hear to us, but I mean, to the wider public, especially to the skeptics.
There's no forum to discuss any of this to the wider public. And skeptics aren't paying any attention. They've moved on to other battles. There are no skeptics participating in discussions with anybody in the field these days.
Well, have you gone back to the Danish researcher who's been comparing bibliography and brought it up to him?
He's not really interested in interacting with people in our field. I have exchanged emails with him, but not on these points.
I have, and it's not going anywhere.
Any discussions with historians of science?
A couple. This is not a popular.
As it was the turnout today.
There's twice as many people here as I thought there would be today. I consider this to be a success. Let me talk a little bit about loading requirements. So we see that there's one off-dehedral site for palladium atoms in the FCC labs. In palladium with no deuterium, all these sites are empty. So you can imagine a situation where you go between having them all empty, all unloaded. So you can define a fraction of the available sites to determine the loading. So for example, the loading is the D to PD ratio, number of deuterium over the number of palladium atoms in the lattice. And this turns out to be an important parameter, and it's going to be the focus of our interest for the coming talks. Now, Fleisch and Pons understood even before 1989 you needed high loading in order to see XOC. In experiments at SRI, they found that you had to be in a loading of 0.95 or thereabouts. That the the cathode had to experience a loading of 0.95 or so in order to see excess heat. So for example, here's 0.95 here. Here's the results that are positive. No positive results down here, and positive results here. Red is positive results at SRI. Green is positive results at the Neofrascati at the time that this plot was produced. So in many labs, it was also found that if there was going to be an excess heat burst, at the time that the excess heat is produced, the loading had to be about 0.83 or higher. So here's an example. So here's the loading. Here's excess heat from a 1994 publication from SRI. Basically, there's no excess heat at low loading, and the excess heat is seen to increase as the loading goes up. So a lot of people found this to be true. At the higher loadings, you get excess heat. At lower loadings, you didn't see excess heat. So as a result, we know it was understood clearly in 1989 by people that were serious about that. You have a loading requirement. So this motivates us to go back to the early negative experimental results and to see, okay, so in 1989, not much was known about the experiments, especially those that got in really early to do their experiments. So as a result, we now know we can, with hindsight, we can go back and we can look and we can judge these early papers to see what kind of loading they got. Now, the very first thing we're going to do is we're going to filter them to see whether they even mentioned loading in their paper. Or not. Well, let's not set the bar too high first. So as you recall, we were at 39 papers. So now what we're going to do is do a filter to see whether the paper even made an effort to think about loading at all. We're down to 22. So a significant fraction of the papers weren't even aware of loading as being the most important determiner or predictor of positive results. So now, suppose we say that they had to reach a loading of 0.83 as sort of a minimum level that was observed in order to see excess heat at all. They still got 7. So it still proves, well, I don't know what it proves, but it, the argument's clearly a little bit weaker. Now, the SRI requirement is 0.95, so theoretically we ought to filter out to only regard the negative results here that reach the loading of 0.95 before you take them seriously, because only those are the ones that would be relevant. Well, instead of going at 0.95, let's go to 0.90. So 0.90, we're still not in the position where we're going to expect an excess heat result. We're down to 3. So of these 3, some of these are actually quite good experiments. They're very interesting. I think this is Quickenden and Green and Quickenden. I think one of these is a German lab that did a really good job and so forth. But now, finally, we can take a look. So we start with 217 papers with negative results. We can pour through them, and with hindsight, we can say, how many of them would we have expected under the SRI criterion of loading to have given us a positive result? None. So these early negative experiments, the need for high loading. Now, loading's not the only requirement. There are other things you need to get a positive result. But the need for high loading is not generally appreciated in the early days in the field. Nate Lewis was asked by Bob Huggins on this point, and Nate Lewis's response was, there's no question the rods were loaded, there's just no fusion going on. Let me note that Nate Lewis and the Caltech experiment didn't get a high enough loading to show up on this graph, nor did the MIT experiment. So in none of these large number of negative experimental papers, is there a single one that, if you were at all honest and straight out and given what we know about, there's none of them that you would have expected to see a positive excess heat result from. Let me pause for 20 thoughts.
I'm sorry, what was that extra filter that took you from the 3 left to the 0 left?
Going from 0.90 to 0.95 by itself gets us to 0. And if we were to add any of the other constraints that are,
I think it says 0.95 gets in there.
As I recall, the issue of loading came up fairly quickly in response to the negative experiments.
yeah, if you look at the literature at the time and you say, well, what's a well-loaded palladium cathode? You would find that if you got a loading of 0.75 to 0.8 in the literature, that's considered to be very well-loaded cathode.
And when did SRI determine that it was 0.95?
Years later.
Years later. So even though the issue of loading came up, the extent of the range of what loading actually wasn't determined until much later.
Right, but it was understood in terms of over potential or relative potential relative to a reference in the Fleisch and Pons experiments. And shortly thereafter, when the resistance ratio was introduced, it was understood quantitatively.
And has anybody gone back to look at what the original Fleisch and Pons experiment, what the loading was in that?
They didn't do a resistance ratio measurement. They did reference relative to the reference electrode, which was misinterpreted by Fleisch. It would be nice to go back and closely look at that. That hasn't been done. Anyway, we're now motivated to understand the experiment. So there are positive results. The negative results we now can look at and understand a little bit better. We see that they're much less significant than advocated by the skeptics. We're interested in the loading. We're interested in what makes the loading difficult. We're interested in why we need loading. We're interested generally in the science associated with palladium deuteride. So I'm going to do a little bit of the introductory discussion. The hydrogen gas could be absorbed by palladium, as due to Thomas Graham in 1866. And I was looking over the old papers. Graham was a very active chemist back in those days, with lots of papers on issues. The notion of occlusion by hydrogen gas in the metal, and so forth. First relevant theoretical understanding of statistical mechanics was done by Latcher in 1937. Interesting that the discovery that you could load hydrogen into palladium electrochemically was Michaels in 1939. As it turns out, this was referenced in Wikipedia. I went down and tracked down the paper that cited this, but getting Michael's paper, getting this paper seems to be tough. I don't know this paper yet. The early development models for electrochemical loading of metals, generally hydrogen, took place between about 1938 and 1952. That continues to this day. Bacchus was the first one that describes a hydrogen evolution reaction in these experiments. So start down the path. We're not going to get very far today, but if you load hydrogen, the lattice constant increases. And it increases by a lot. It's like 5% increase. Here's a loading of 4.08. And 0.6 is 402. It actually goes down here to about 0.387 or so. So 387 is way back down to 0. Yeah, I guess 389 is the number I'm using. So it's a 15% volume increase, which is very large. It's about the most intensive thing you can imagine doing to a metal. You're stretching the bonds apart, by such a large volume increase. Loading other metals with hydrogen also gives a volume increase, so this is not particular to palladium. So here's a table of volume increases for hydrogen for different metals. Palladium, nickel, tantalum, vanadium, niobium. You get similar numbers, so there's nothing special about palladium. And you imagine that you put in the palladium and stretch it out. As it stretches, you're going to need more energy to put in. That means that you would expect it to be harder to load the more hydrogen you put in. And that brings us to the phase diagram. Phase diagram looks like this. This is the loading. this is the pressure. So the idea is you're leaving a piece of palladium in a gas and you're letting it come to equilibrium. And if you do that, you get these isotherms. So here's 20 degrees C. So with pressure under 100th of an atmosphere, you can load to 0.6. And this is flat. This is called the miscibility gap, which we'll talk about next time. And then once you reach the edge of the miscibility gap, you go up. So you have to add more and more pressure, and it's a logarithmic. So you need factor 10, with a factor 10, and a factor 10 to get the loading to go up. So this is telling you that it's harder and harder and harder to get high loading. That tells you a little bit that there's a really good reason why people have trouble getting high loading needed. If you change hydrogen to deuterium to tritium, you get a change. And this effect has to do with the 0-point energies. It's nothing particularly special about the different elements. It's physical chemistry issues. In order to sort things out, I'd like to have runs. I'm looking at the clock. I'm thinking, let me give time to Mitchell. Let me pause here because I think this is good enough for today. The message is that we know from the phase diagram that it's very hard to get high loading. And we'll quantify this and think about it, dig into things starting tomorrow morning.
Peter, you mentioned that 15% increase in volume. At what loading was that?
A loading of one.
Of 1. Okay, got it.
Now, the interesting thing is when we see volume increases of 15%, we don't see the excess heat. I mean, if you really want excess heat, you want to load and you want to get 7, 8, 9% increase. So are they counting structural defects in that number?
No, this is only non-defective material. I'll be talking about those issues. Anyway, let me repeat my warning. This feels a dangerous field to be in. Can turn it over to Mitchell. Should we take a bio break for a few minutes?
Okay, 5-minute break.
15-minute break.
15-minute break.
I like that. Let me knocking off all the negatives up here.
We
have 8 viewers online.
It is. We didn't do that last year, right? That's just
No, yeah, it's new.
that's terrific. I really like that.
I mean, I went through, collected as many papers as I could.
Is that extremely time consuming or?
Yeah. That took a long time.
On the palladium side, just trying to recall, it's been stated in the past that some materials will exhibit excess heat in experiments and others won't. Is that those materials can and cannot based on their properties, or is it that they certain materials can't be loaded to 0.95, and if they can be loaded to 0.95, they're highly likely to
So
exhibit?
it turns out at the beginning of this talk tomorrow, we're going to get into that. I'm interested in more detail there.
Okay, fair enough.
And what?
Okay, just a quick question about the 49 positive papers versus bibliography. So sorry, exactly, but there's 49 positive papers using palladium, chemistry, and calorimetry. When you apply the same loading and deuterium,
Yeah, I think so.
how did those papers?
Most of them reach the and not very many of them.
That's a live broadcast.
It's going pretty good.
Yeah.
Yeah, we're live right now. We got 9 viewers here online watching us right now. Hey, how's it going? We're taking a 15-minute break right now for those of you who are just tuning in. I'm gonna go get some food real quick. I just want to put up a message so if other people do tune in that they know that we are doing a break right now. I don't know how to. I should be able to draw something on the screen. No. No, I can't really. Type on Google Effects. Anyways, I can't. I'm trying to figure out how to put a message on the screen. I might just write a little message up on the board, so if people do tune in, they'll know that we are taking a break right now. So they aren't too confused. All right, I'm going to turn this back around. Yeah, it's fine. I think we could write something on the board just to say back in 15 minutes, because I could break the live stream, but I don't want to lose our viewers. We got 4 people online right now. 5. Another one just signed in.
Mitchell presented something on the screen share. Yeah.
I just write it on the board.
All right.
Back when we do the break, so people who just tune in to the live stream will be like, won't have it. They're like, oh, what's going on here? Why is there nobody here?
Confirm their regional.
The thing that's really screwed up about it, right, is here on my screen. Here on my screen, it looks backwards.
Yes.
It looks reversed.
Yes.
So I thought it was reverse broadcasting to everybody. So I went and tried to fix it. I ended up crashing because I was screwing around with the settings and control panel. It crashed. So I lost like 5 minutes after I recorded the first 20 minutes, then I lost 5 minutes of Peter in there because my computer crashed. Then I reloaded it and I had to I went and I installed the proper Logitech software in the drivers for my webcam so I could get that option to flip the mirrors back and forth, because there's no way to do that here in Google Hangouts or through YouTube. It doesn't give me a way to do that. So I went to try and download the original software and drivers so that I could flip that, and then I ended up flipping it, and then I got the call saying it's reversed now. So it was fine, even though it looks reversed and backwards on my screen. They're seeing it right. So like here I am thinking I'm fixing it for people, and I went and broadcasted it in reverse, and I broke it. So my buddy, Ruby actually texted me and was like, "Oh, it's reversed," and I didn't know if she was talking about the old one or the new one that I'm doing.
Because it's right after you did the transition.
So it's right after the transition, and then she's in class teaching right now, so she can't reply back to me. She didn't reply back, so I had to text my other friend and have him load it up and tell me.
Yep.
And he said it's also the audio was a little too high and it was clipping, so I had to turn my microphone gain down a little bit to fix that. So hopefully we're all set now. I kind of had a feeling some of these things would
Yeah,
happen.
it looks like a little bit of that real-time feedback is really important to get that.
Yeah.
So someone's looking at it from outside.
Yeah, so hopefully it's all set. I was gonna stop it, but I'm just too afraid of getting it working again and losing all our viewers and stuff. We got people tuning in and watching us live. So I didn't want to lose them. So anyways, that's for those of you who are tuning in. We're taking a quick break now. I had some issues with the screen forward and reverse on the earlier part of the video. I hope that wasn't too much of an inconvenience for people watching. Hopefully we get that issue figured out and fixed now, and everything should be working. So
How many people are logged in?
we have 6 viewers live right now watching. And if I get it, I got a couple questions from them, but if we get any live questions, I'll try my best to ask those for the people. Because they don't. We got 8 viewers. I'm just going to leave this going. I'm going to go grab something to eat real quick. I'll be right back.
Oh, it's a quarter of. Okay. Yeah, this can come in a bit later. We actually have homework I'm putting out from my side. And all you have to do is read. What I've done is I've got about 60 publications. Peter may match me here too later. But I've taken the first 10 and put them on the internet. And it's in a folder such that I'm going to hand these out. And if you email me, I will send you back the URLs and you can click and download all the papers. And that will be a lot of what we're talking about here. So let me hand these out here. This one through. Also, I had a course question because I'd be curious what people think. And I'm going to answer them anyway, which is one, does anybody think the lattice is important? Does anybody think the lattice is not important? Okay, that's good. And does anybody think cold fusion is fusion by electrolysis? No? All right. Anybody think cold fusion's low energy? All right, we'll move on. Anyway, that says what to do with it. A lot of the material that I will relate today has partially or fully been covered by Peter, so you'll have the advantage of seeing some of it twice before we branch off. Today I'm going to talk about an overview, a little bit about electrochemistry, the materials, and the importance of doing controls when you do experiments. And I find that is the biggest lack in what's going on recently. A lot of the older experimentalists, Lex, Cravens, Mel Miles, the people at SRI, McCubry, and ourselves, we spend a lot of time putting controls on. And some of the recent people that we're seeing, like with Rossi and Lugano, there's a little bit less control. And hopefully, after seeing this, when you do your own experiments and efforts and works and develop your systems, you'll find it much easier. Tomorrow we'll talk about aqueous cold fusion systems, and I'll show you the equations we use for controlling them. Despite the fact that people think there's no theory of cold fusion, there's actually several good theories. There's theories of loading, theories of measuring that loading, theories of understanding the conduction through it. Peter will show you the theory of how you can get a coherent transfer from the excited state of helium to the lattice, so that when the helium comes down, we end up with helium-4 that's fixed in the lattice. Then we'll talk about the latest dry nanomaterials on Thursday, and Friday we'll finish up with all the rest if there's enough time. So the first question is, why is cold fusion important? And the answer is it's energy. The answer is we need quite a bit of it, on the order of 100 watts per year. The reason we need cold fusion is we can't trust oil because of pollution, because of the problems that accrue. I happen to think that the pollution that we get from this is a lot worse than global warming. Global warming may kill us in a century, and the pollution may do it much quicker, as well as causing these climate changes. Tiny amounts of oil on the surface of the oceans are having massive effects. So anything we can do would be an improvement. Nuclear has its problems, as we know. And as a recent paper in IEEE by some people at Google showed, solar and wind really haven't done that well. And if you live in Massachusetts, now you're paying your electric bill for wind, and there is no energy coming out the other way. So this works quite well. We often have people come to the class who at their homes, they have geothermal, but it's hard to do, or hydroelectric. It's very rare. This was the paper that came out with from Coningstein and Fork last November, showing that when they finally looked at wind and solar, it just was not cost effective and did a lot of problems. So what do? We just break the Coulomb barrier. We spent a lot of money on it, as you know. But when I first came to MIT, I was going to work in hot fusion. That was 1966, and they're about where they are now, except that we get more output. We're already, as I'll show in a little bit, making probably more excess heat than they'll ever make, and we're on the edge of making electricity as well. Peter talked about that. We have the cross sections here. The reason hot fusion likes this is it happens a little bit easier at lower temperatures. We can skip all that. What is the light at the end of the tunnel? As I saw it in 1989, and as you see it today by being here, it's cold fusion. So what is cold fusion? It's the conversion of hydrogen, either protium or deuterium. We think it's mainly deuterium to helium-4. And there's a few definitions. Excess energy is the amount of energy we get out, which includes heat, above what we put in. So if we take the ratio, we do the subtraction, we can either get the incremental gain if we take the ratio. If we do the subtraction, we get the excess energy. And we do a lot of work with controls. And the NANOR device, it's a little two-terminal device. It looks like a resistor. It has cold fusion active material inside. It's preloaded. Those are the NANORs that we use, and we'll talk about that in a bit. The reason cold fusion has great hope for the planet is that it's abundant. Deuterium's everywhere. Not so much in the sky today, but on a normal day, it's everywhere. It's safe. It does not produce CO2 or other radiation, as Peter talked about. Therefore, it's pollution-free. So if we were to substitute a city like Boston that's producing this many tons of CO2 and sulfur dioxide and nitrogen per day, per gigawatt, Boston does about 5, we could convert that to just make 4 pounds of helium. Big difference in terms of contamination. And as Peter talked about, the energy that we get out in terms of energy density at cold fusion is very high, much higher than explosives or foods. Explosives, as you know, are a little less than the donuts you're going to eat today. But that's because we take the energy out of the donut slowly, as opposed to the rapid transfer of energy here. But our energy density is phenomenal. In the case of the NANOR, if we plot energy density out here, and we plot power density out here, here's our standard energy conversion and energy storage devices, and this is where we are with cold fusion, way out here. Several of you have coffee. We drink coffee because we like caffeine. Caffeine is approximately 500 micromoles in an espresso. You have 900 micromoles of deuterium in your espresso. If you could burn it with cold fusion, that gives us approximately 566 megajoules if we were burning the deuterium in your cup of coffee, which will give us, at a 1 watt rate, enough output for quite a few years, more than you'll need for your watch. And if we took it up in an airplane at a rate of 80,000 watts to get up off the ground, we could fly for about 2 hours just on a cup of coffee. And what's our product? Cleaner water. I mean, how could anybody not jump? They should take the money they do in hot fusion and take a fifth for this, if not a half. All right. And if we do an analysis by commercializing, basically, if our energy in terms, even if our refills were on the orders of $25 per refill for deuterium, we still end up with a cost per kilowatt hour just a little bit over a dime. And if we can get the cost of the refills even lower, because we're essentially dealing with 1 in 6,000 parts of water, we can get below a dime. And this is where we are right now. The problem with solar and wind is they can't get below this. We have a chance. And that includes if we charge for the driver, and deuterium, it's even better. We can talk about this more later. The take-home point is the excess energy from cold fusion is greater than what we put in. It's clean, 0 carbon footprint, no pollution. Questions? None?
Question here.
Yes.
You mentioned that protein and deuterium.
Yeah.
So earlier, sort of this slide indicated that light water can be used as a negative control.
Excellent.
So, what fusion, if any, I could see the protein, and to what extent do those contradict each other?
Great question. First of all, there's only been one experiment where anybody looked with pure water. It is pure H2O. Nobody does. We use ordinary water. So we're dealing with, in most experiments, when we show, we call it light water, it really isn't. It's really ordinary water. We're still trying to resolve out what the reactions are. And Peter will talk more about it with the Bass experiment, with the Bush experiment, and I'll show you the impact of adding D to ordinary water. But it's a great question. We're still trying to resolve what's going on there, especially with the nickel. Yes.
Oh, sorry, I had a question here from Daniel Hack 8878. He says, for his question is, there are 2 main types of cold fusion setups. One is the ECAT of Rossi, and the other is like Flines and Fleischmann and Pons. So how are they related and how?
One's wet, one's dry. We're going to talk about the wet stuff on Tuesday. We'll talk about the dry stuff. I mean, the wet stuff on Wednesday, the dry stuff on Thursday.
All right.
Okay, what I'm going to do here, before I get into the calibration, the materials, and then talk about what we actually measure and what's emitted in terms of excess heat and other particles from cold fusion systems and palladium with heavy water and nickel with both heavy water and ordinary water. I just want to review what happened over 25 years, because there's been a lot of changes: diversity, development of systems, verifications, thermal power spectra, output, materials, nanomaterials. For a field that doesn't exist, we've had a lot of traction and a lot of development. And just like Google did a few things, a lot of, just at JET, we developed a lot of things. Optimal operating planes. We shared code deposition with Spay Wars, and we developed these high impedance devices I'll talk about, the fusors. These stand out for me in terms of performance far above the Fleischmann-Pons system. And we'll talk about that, and we'll talk about the dry preloaded nano systems. Now, here's where we are with cold fusion. This is 1989. We had early demonstrations of excess heat. We're up here around second base. We have reproducible heat, and we're working on trying to get the third, which is to make electricity production. But the real home plate that we want to get to is where we have break even. And of course, that's the dream of hot fusion. They always tout it, but they're not even here yet. So let's talk about diversity of systems. When Pons and Fleischmann came out, Peter showed you the cell here. They then went on to this. They put a series of videos out where we can show time videos. We developed the Fusor, which is in a heavy water solution, which is free of all other ions. And that's why we call it high impedance, is most people who do cold fusion have an aqueous solution that might be between a milliohm and a couple of ohms. Our solutions run between 100,000 ohms and 800,000 ohms. They are high impedance. And the nanors, which are shown here, are even higher. Some of them up to a gigohm for input impedances. We understand more about the metallurgy. We understand when we co-dep, we get a series of structures on the surface. We understand that sometimes we can get a Vulcan-like reaction from the surface, and it's unclear. We think this may be from the reaction itself. The Japanese have developed here for Mitsubishi, making very complicated surfaces. We're in the palladium, we'll have maybe calcium oxide or magnesium oxide, and this is a far cry from what Fleischmann and Pons initially came in with. And each of these areas that may be active, we now believe that, for example, here in the Fusor, we may have a region where they optimally give off their excess heat, and we'll show you that. We've developed some nanomaterials, which I'll talk about on Thursday. Here we see this is input, power in this direction. Here's our energy here. So we put an input to the control, we get an output in red, which matches. We put the input to the nanor, we get more out. And this was in fact, this one may be the demo that we did at our class 2 years ago. So we understand metamaterials. Now, metamaterial, when I went to MIT, we learned that there's a diversity in materials and they have their own scientific properties. In the last decade, we've learned that shape matters. And in the case of optics, we found that we could make materials where their properties would change by their shape. And we found that too here with the Fusors. This is looking down on a classical Fleischmann-Pons system. We're going to talk about this tomorrow, where here's the anode, the cathode. They hit equilibrium very quickly. And that's why I think it doesn't work as well as ours. What we do is we actually have an electric field going through the metal. And so we're ending up getting a flux. I think that it takes more than loading. You need an active material free of cracks. You have to get the high loading that Peter talked about. You have to put in a flux, and we'll talk about that tomorrow. And see, here's some of the early work when we were looking at excess power as a percentage of the input. Most materials are negative. They don't give excess heat. Some of the nickels do. But this one stood out, and those were the coils, and these were the precursors to the Fusors. We developed controls. We use ohmic controls. I will not do an experiment without putting some kind of control in, because what I want to do is, for that calorimeter, for that system, I want to know what the output is into an ordinary ohmic device. That's our thermal control. Then sometimes we'll do dual ohmic controls. We'll have two calorimeters. I'll show you this tomorrow. When we use Stirling engines and propulsion devices, we'll set up, in addition to the cold fusion device with an ohmic control in it, we'll set up a complete second identical calorimeter with an ohmic device in place of the cold fusion device. We'll run them in electrical series. So now we have the same current going through both. We can measure the voltage here, and what we find when it's operating right, we'll get less power going into this one, and you'll see the Stirling engine is flying. That's a dual ohmic control. And then we use metallic controls. I think it's really important to have non-active materials to show that your system is calibrated. And now I'll show you, we have something new. We have nanomaterials since the last course last year that we've developed that shut off. And so we're actually able to drive them through excess energy, then bring them back to like an ohmic resistor. So we have a third control that's on here, a fourth control. So let's look at some of these as they appear at heat. This is a palladium heavy water system with platinum as the anode. And what we're looking here is a function of time. We're going to alternately take the electrical current and put it into either the cold fusion device or an ohmic control. Here's an ohmic control. Here's the cold fusion device. So we measure the power in, and for the same power in, we're getting more temperature out from the cold fusion device. And you can see we haven't reached equilibrium with this yet. That's what we also like to do, is reach equilibrium so we can judge these systems and judge them together. Here's one of the diffusers. This is driven as a cathode, so the anode would be over to the left, and what we get is bubbling where the electric field comes into here, and here's our delta T that we're coming out. So we start off at a temperature, say 23 C, and we find that our temperature is going to go up here to 60 degrees, 80 degrees, 90 degrees, and here's our ohmic controls. Yes?
What's the cathode material?
The cathode here is palladium if it's heavy water, and nickel if this is heavy water, so that would be palladium, always palladium.
And there's also palladium.
Pardon me?
There's also palladium in the solution.
Not unless it's co-depth. I tend not, when I like to show excess heat, I like to show high power gains. I like big temperatures. So for me, cold fusion lost its excitement in '89. It turns on rapidly, as you'll see tomorrow. It'll turn on in 20 minutes instead of 2 weeks. But we don't get the massive energy gain out that we do with the high impedance system. Here, for example, is a dual ohmic control. This is what we showed at the open demo in Peter's office in 2003. Here we can see the palladium cathode. Here's the platinum anode. This is unfilled. So we fill them both with water. And here's the ohmic control. We put them in electrical series with a current source. It's very easy, simple experiment, well characterized. And we were able to show with less power, with less voltage across there for the same current, we had a higher temperature. And we were able, in his lab, for 5 days to show a energy gain of 4. And we'll show you some of that data. So we've had improvements of verification. Right now, when we measure excess heat, we measure rises in temperature, we'll measure heat flow, we'll do full bore calorimetry. As a minimum, we'll look at 3 things. We'll also do time integration to rule out false positives. We do noise measurement. A lot of people in the field don't. But I like to, because one of the things we discovered back in '89, '90 was if you drive below the noise level, you're going to pick the noise up. You're going to think you're getting excess heat. So you really want to know your calorimeter. You want to know its response. You want to know its response to an ohmic control, and you want to do a noise measurement. So here's this is a cartoon of one of these calorimeters. When I make them with good geometry. Just like you'd use good geometry in optics, you want to use good geometry when you do thermal measurements. So you use fire bricks. We'll have the heat going in one direction. We'll measure the heat flow through that one direction. But from a cartoon, what we're doing here, we have an electric power source. We'll have a control right next to our temperature measurement device. And so we'll measure the temperature within this volume. We'll determine the amount of heat because we know the mass, we know the specific heat. And we'll also measure the heat flow. And you'll see this over and over. Those are parallel verification. We also do serial verification, where we'll measure, we'll generate a delta T at the core of cold fusion, and then we'll have it go through a series of devices, either to pull out electricity or to do motion through a Stirling engine. And that allows us with paired systems, either paired thermoelectrics or paired Stirling engines, to get additional verification that we're getting excess heat. So for example, one of the things I sent to the patent office was we showed we had excess heat by delta T, by heat flow, all independent sensors, by calorimetry, by electricity, and by motion. And of course, they didn't read it. They said you're doing the same thing. Fleshman and Pons does it. It doesn't exist. Another thing we do, which we'll talk about tomorrow, is I like to ascertain how good a calorimeter is. One of the things I learned back at ICCF7 in, I think it was 1997, was some people who do work in the field set up calorimeters that don't even give a real response to what they're measuring. So what I do now is I want to see if I put a square wave in, do I get a square wave out? It sounds so simple, but it turns out it's important. And a lot of times you don't see that. So for example, the Japanese at ICCF7, they had just given up. I think this was at Technova on doing cold fusion with Fleshman and Pons. And I spoke to them, I said, why?
And they said, well, we have one calorimeter that shows excess heat and one calorimeter that doesn't. And I said, well, can I see your calibrations of the square wave? And they were very nice. They said it to me, and the one that didn't show excess heat showed singularities. They never even got a square wave back. So what we do now is we want to evaluate the calorimetry. Is it really accurate and quantitative and coming back? And then we do one other thing, which is most people, when they measure heat flow, they measure T2 minus T1, which is the standard way you're taught in graduate school. And that gives you this curve. And one of the things I found out was there's a second term. That's the difference term. There's a T1 plus T term over T2, and that handles the absorption of heat by the calorimeter itself. So that's this term. And when you add them up, you get really nice. You'll have that paper in your mailbox if you send me the email how to do that correction. Here's the measurement that shows why you do not want to operate in the noise level because you get a fake excess heat. Okay. We don't believe the results unless we see verification by multiple types of sensors. And that's basically the material I'll be showing you for the next 2 days. So for example, here's one of these. Here we're looking at, this is a palladium heavy water platinum system. And here we put the input power to the control. This is 2 watts here. Here's our output. A little time lag and we get it back. And here we put it into the fusor. These are the coiled cathodes in ultra pure heavy water. Ultra pure will cost you, heavy water runs about $250 to $500 a gallon. If you get it ultra pure, it's about $3,000. And what they do is they remove the paramagnetic elements. And the reason I don't like paramagnetic elements is when you put an applied electric field intensity on a solution, everything in the solution is going to deposit on the cathode that's positively charged. And the problem is heavy water is laden with all kinds of group 8 materials. And they end up having, they create bubbling sites on the surface. I asked you before, do you feel that cold fusion is cold fusion by electrolysis? Nobody answered. And the answer is most people say yes. Almost everybody says yes, and they're wrong. As I'll show you tomorrow by the equations, it's 1 minus electrolysis. So when you really understand the equations, you don't want those materials on the surface. And it turns out it doesn't, here we have the control and the fusor. It doesn't matter what the order is. Here's the fusor, here's the control. And what we find is when we have an ohmic control, these are the energies we read off on the right. Power is read off on the left. We're going to see the same thing over and over. And when you have an ohmic control, these are going to rise in parallel. That is the energy you put in is the energy you get out. But when you have real cold fusion, they're going to separate. And so here's our power gain. Here's our excess energy. Okay, questions? Okay, we'll come back to it. And this is the one that Peter showed. Popular Mechanics came by in 2004 to take a look at this. And this was what they put in their magazine. So here we have a control, a control, a control. And here we're running the fusors at 2 different levels over about 4 or 5 days. And you can see over and over, we're making quite a bit of excess energy here, around 400,000 joules, and our power gain is here. So there's no power gain for the controls. There was a power gain for the fusors. Now, here we have, this is a dual ohmic system. I'm going to go over these in detail tomorrow, all of them. But I wanted to show you today some of these, just so you'll start seeing what we're looking at here. We're looking at the power here, the energy here, and this is time. We have 2 identical calorimeters. So what's happening is one calorimeter has an ohmic control. It's getting the green input. That's the energy. Here's the energy coming out. These are parallel matched. There's no excess energy. Here is our input to the second calorimeter that has the cold fusion device. This is a palladium heavy water platinum system. And here we're putting in the energy. There's a lag. And here's our power gain. And here is our excess energy. And what's interesting is there's heat after death. The advantage of good calorimetry is you can see phase change. We can see the endothermic loading. When you first put heavy water on palladium, it's very easy to get to a loading of 40%. You're going to pay to go up to 0.85. And here we see it drops down. That's the payment. And here's what we get out, this energy, plus the heat after death. We'll talk about more of that tomorrow. These are nickel ordinary water systems. Here's nickel as a cathode with a fusor. We found, again, the best way to get cold fusion are with these fusor devices in a high impedance system. So we have ordinary water with no additional electrolytes. We're not adding sodium or potassium or lithium. We're using conductivity water. What a bad name that is. They call it insulating water. It comes out of the system at about 18 megohm centimeters. And usually over about a day, it'll drop to 1 megohm centimeter. And the reason is CO2 enters the water. And the CO2 creates a small number of ions in the system. And so here's our remote control, nice noise measurement. Always do a noise measurement. Here's our output, input. Here's our input to the cold fusion system, and our output is higher. And again, we see there's a match here for energy and a superlinear response when we really get excess heat. Here's another one. This is nickel with ordinary water and platinum. Again, noise measurement to show we're above the noise. Input, output, a little less. Here, we'll put a few controls here. But again, when we have an active system, and we deal, and Peter will explain, it's much tougher to load the nickel. But when we get sufficient loading, we get the flux, we get the excess heat out. Okay, the other thing we've seen over 25 years is we get increased output energy density. This is what Pons and Fleischmann initially announced was 7 watts per cubic centimeter. And we're way above that now. Nuclear power rods are about 100, and we have exceeded them. In terms of energy density, this was the graph I showed you before of the NANR. We're way outside where energy devices are. And we've looked at a lot of materials. Going back, it's 25 and 3/4 years now. We've looked at palladium and a whole number of systems. These are our gains. We've looked at nickels, and what we're going to show you today, which you haven't seen yet, last time we reported the NANRs had power gains of 20 to 80, and we've gone a little higher with some of the newer ones. There's a lot of working theories. These were summarized by Dave Nagel. And this is what I got into cold fusion the day of, because I envisioned, having studied ordinary water with Dr. von Hippel here for years, and having made devices that move protons around in ordinary water, that maybe this equation would allow me to get increased loading. I felt from the beginning that the secret to cold fusion was to get a high enough loading to get what we thought were band states, where we would get the desired fusion reactions. But this is the equation we're going to talk about tomorrow. It says that the flow of deuterons is a diffusive component. This is down the concentration gradient. This is diffusivity. And there's an electric component. So dV, dZ is the electric field. This is the electrophoretic mobility, and that's times the concentration. And if we take two of these equations, one for deuterium, one for palladium, take the ratio, that's how we got co-deposition. We'll talk about that tomorrow. And so a lot of people do co-dep, and the advantage is when you look at loading, you see, it's very hard to get high loading. This is where it's a loading of 1 with a classical cold fusion system. But if you do co-dep, it comes up right away. That's the advantage of co-dep. We can skip that. We can skip that. This just basically shows that just as the impedance shows you the loading in palladium as a metal that you're dealing with in aqueous systems, it turns out it's also true in nanomaterials. There's a peak, and after you hit the peak, it goes down. Over the 25 years, as Peter mentioned, we've done the impact of photoirradiation of the cathode with single and double lasers. For example, here is the control. Here's the control plus the laser. And we put the fusor on. This is our excess power gain. And we put, this was 30 milliwatts. we're going up, again about 300 milliwatts by putting on a 20 milliwatt light right on the device, which you can see over here. We've learned how over the 25 years to control these devices with what we call optimal operating point manifolds. Let's take the Fusor and look at, this is from 0 to 8 watts input power. We look at our excess coming out, so there's no excess coming out from the controls, right? They're all below. But when we look at the excess coming out, once we hit about this input power, we start seeing it. It goes up to a peak and comes down. We think this is insufficient loading and flux. We think this is wasteful electrolysis. But for whatever the reason is, if you're an engineer, this is where you want to drive it. So I think one of the reasons that we have so much success is we analyze our materials, we analyze our systems, we figure out the optimal way to drive it, and that's what we do. And then also another reason we do well, I think, is over the years we've learned that there are things that quench and contaminate. I mentioned one to you, that we use and have developed a high impedance system because we don't want a cathode fall of materials that cause electrolysis. I've told you electrolysis is bad. You don't have to believe me. You'll see tomorrow it is. But that's a way to quench the system. I mean, you could spend all the money you want on building a cold fusion system, but if you quench it, you're screwed. Here's another quenching that I'll show you tomorrow. This is a nickel nanomaterial, nanor, loaded with D. Okay, I mean, if there's ever a question of Ni interacting with D, a lot of discussion on the net, well, Ni only works with protons. Well, that's not true. Here, we're driving this at around 1,000 volts. Here's our aroma control. The way to find this, we're looking at the delta T, the rise of temperature divided by the power input. And the reason we do that, the reason we take the ratio, as you'll see tomorrow, is you can take the ratio of the two to get the power gain. Okay? So if we take, here's our input to the ohmic control, here's the delta T over the input, here's our input to the nanor, this is time. And when we take delta T over the input power, we get this. So our power gain is this. And one of the things we do now, the additional control we use, in addition to calorimetry controls, thermal controls, is we bring them down. Here we avalanche the material. We'll show you that, how we do that on Thursday. And it becomes like an ohmic resistor. So we have yet another control, okay? We have the control of the fact that we have control, an ohmic control. We have another control that we can bring the material back to a non-cold fusion state. Reversibly, by the way. We know now how to bring it here and then back to where it's operating. This is the impact of adding heavy water to nickel, ordinary water. Here's ordinary water. I think this is the only experiment that I know of where people have added heavy water to ordinary, and we find it does increase it. And here again, we talked, this little section's on quenching. Not only can you inadvertently quench the system, here we quench the whole nanors. Once we apply, when you take nickel and you either drive it too high or put too much heavy water and you change the structure, the color changes. See, it goes from bright nickel to this dark. The resistivity changes, if you could read it. It drops from 8.8 microcentimeters to 8, and then it never works again. So there are reversible quenchers, there are irreversible quenchers like that. And the other thing is we've developed an awareness of the emissions. Now, SPAWARS has done an incredible amount of work on the very low level emission of high energy penetrating particles. I'm going to skip that. You read their papers. What I have done is we've looked at near infrared. And so here we now put cams in. We do optical cams, infrared cams. And when we get cold fusion, we see this bright near infrared coming out. We also found that with the nanors, we got very low level ionizing penetrating radiation. We're not really sure what it is. But following the lead of SPAWARS, that's Pam Boss and Frank Gordon and Larry Forsley, we began using CI39. So we laid a CI39 over the nanor, drove it for 3 days, and it turns out that we imaged it. I don't know if you can see this, but this is the nanor. This is the one that's a control. We take the ratio, we see this, and we've imaged it. The fact is cold fusion is very reproducible if it's done right. You use the right material, you avoid the quenching, you get the adequate loading, you get the adequate flux. If you use the right equations, you can, I mean, if it was not reproducible, they wouldn't be able to do demos. And we've had a lot of demos. Dennis has done demos. Peter showed you that we did demos here at MIT, including John Dash. And then we did the most recently at this course a couple of years ago. And since then, we've been developing better nanors. This was the nanor from the course. This is our input power here to the control. Here's our output temperature. Here's our input to the nanor, output temperature. And remember, and here's the calorimetry. Input, much greater gain. And we see here's our excess energy. So over the year, I find there's a lot of successful cold fusion engineering. We've got diffusors, we've got optimal operating points. I might show you Thursday or Friday how we control heat after death. The M nanors are really good, and I like our data analysis, which we'll show you. We've also been developing applications. So the Stirling engines will show you. We've done a little work where we, here, for example, pure Stirling engines, the calorimeters are inside. One has an ohmic control, one has the fusor, and we can switch back and forth, so there's no differences in the calorimeters. And what we find is, again, these are in electrical series, so we measure the current, we can measure, how easy is that, the voltage across each. And we can see for less input power, we actually get more gain out. And we're trying to make electricity. We'll talk about that later and what the problems are. We'll get to that on Thursday. So happy birthday. It's 25 years. I don't think it's as bad. I wish it was quicker. You know, this should have been 5 years instead of 25 to get here, but that's what it's been. And the heat does go on. And we'll talk more about it now. Questions? Am I putting you to sleep?
Got 15 viewers on here.
Okay, before we talk about calibration, I'll just go back to the materials.
I've got a question.
Yeah.
Is your nanor and fusor, are they described in the public realm, or is it still IP?
There's a mix. We functionally talk about them in the public domain. We talk about their responses. We talk about some aspects, but there's some IP that's still pending at the old patent office.
So there wouldn't be like you know, a diagram of the working parts and the materials.
I think you'll find those in the papers. You'll find the survey. Materials that we need for cold fusion. These are the fuels. These are the products. Peter will talk more about why our output is commensurate. By the way, since the output is commensurate, doesn't that eliminate Huizinga's third problem? I mean, conservation of energy. If we're getting out the energy here, we can't get it out in the endless. With his argument, but physics does say that. Okay, how many lattices are involved? It turns out in an aqueous system, there's 4 lattices. When you analyze water, as we'll talk about in a bit, there's 2 lattices. There's an oxygen lattice, there's a hydrogen lattice, deuterium if it's heavy water. And in the palladium itself, there's 2 lattices, as Peter will describe. And you really want to organize yourself to understand that, to really get a feel of what's going on. And the electrode materials are here. We'll talk about it. So let's start with our periodic table. We're going to deal with group 8, which is over here and a little bit up here. You all know what hydrogen is, isn't that great? We imaged it last year. Know the isotope by its color. This is hydrogen, this is deuterium. And you know all about all this stuff. You don't need me to tell you. And helium-4, you know all about, probably know less about water. There's many types of water. Ordinary water, 1 part in 6,000 is deuterium. Properties we're going to talk about. Conductivity water is what we use when I describe ordinary water. I'm talking about conductivity water. The reason it's in quotes is it's really high impedance, as I mentioned, 18 megohm centimeter. Heavy water, there's a range of them. As I told you about, some of them are more pure than others. And light water is what we really need to do, isotopically pure H2O. Okay, so water comes together. It has the high electronegativity of the oxygen, so these become partially positive. You end up building structures. I'm going to skip all this. There's basically a lot of structures in ice, and water is 3 of the phases that come together. And these are the lattices. What happens is we're actually taking deuterons from the water and transferring them by a molecular rotation and intermolecular vibration into the palladium to load it up. And water, this is the oxygen lattice, mainly. Water is about 2/3 ice 1, a little bit of ice 2. This is ice 1. This is a picture I took looking down the z-axis. See, the rule is in water, you can only have 1 proton between every 2 oxygens, but there's 2 sites. So what you want to think about is, why does water have a high dielectric constant? We know it floats. That's why the reason we're all alive is that water floats when it freezes. If it didn't, we'd be dead, because every lake would freeze from the bottom up. So if it wasn't for that, we wouldn't be here. And the other reason we're here is that water has an incredibly high dielectric constant. Now the question is why? Most people will tell you it's because, well, the H2O is gonna rotate. You're gonna get a cold rotate. Turns out that's not what happens. It turns out, and we'll get to it in a bit, that these structures, when they come together, this is ice 6. Oh, it's the next section, I'm sorry. I will show you how the defects move. What happens is, when we get to the slides, these protons are going to shift in pairs, and they're going to inscribe a ferroelectric dipole in water. The reason water has such a high dielectric constant is that it really is a ferroelectric material. And what happens over short range is, when you apply an electric field intensity, you are creating a diffusion ellipsoid. And that is what traps the countercharge at the electrode. I'll come to that in a bit. If you want to read more about this, send me your email. The paper is Dances with Protons, and you'll be able to click on it and read the whole story. Okay, so we use heavy water, and this is the cheaper one. The paramagnetic free will cost you a bit more. We use as the anode gold and platinum. Anybody know why? The answer is because it doesn't corrode. The anode is the site of corrosion, okay? If you want to understand electrochemistry, we'll do that in the next section. The one thing you got to remember is anode is the site of corrosion, and cathodes are protected. There's a lot of stories we could go into. And the same thing with platinum, which was not well understood. And palladium is interesting because of the high loading. We'll get into that in a bit. This is important, but Peter covered it, so we can jump ahead. The real issue, the critical issue, is the fact that it loads. And that is the key to the palladium. Here, for example, when protons are put into palladium, you can actually see them by scanning tunneling microscopy. And as Peter showed, inadequate loading never gives excess heat. It is the key. So everything that I'm going to show you is ways of improving the loading. And palladium stands out in terms of its carrying capacity higher than most other metals. It turns out that I am a real believer that although you want vacancies, you don't want cracks. I do not find excess heat from cracks. I know there are people on the internet now saying cracks are the secret ingredient. I think they're smoking it unless they can come up with some evidence. Anyway, when we load, we destroy the palladium. Peter and I took these X-ray spectra years ago. Here's the palladium before loading, and we get back crack after loading. And it turns out it is a real structure breaker. And so dislocations play a role in understanding these lattices, slip dislocations, screw dislocations. Now, I'm not going to have time to go into this. Basically, we think, do you still think the vacancies? Okay, we both, there are some things Peter and I disagree with, some things we agree with, and we're doing experiments to find out what holds. But both of us, without having a lot of final experimental evidence yet, believe that it's the vacancies, that there is an occasional palladium missing from this expected site, and that is where the reaction occurs. And so we have tried to make these with electron beam over in the building over there that's labeled HVRL. And we made them using 2 MV electrons. I gave something like 200 gigarads to do. It was enough to make the wood underneath catch fire. And then we had the vacancies, and they healed spontaneously. So the resistivity comes down as it heals, and we get lattice quakes here. And anyway, I'm going to skip this. The reason that the vacancies are important, we also think that co-deposition makes vacancies. Co-deposition is a double kicker. By having palladium hit the cathode at the same time the deuterons hit, you not only get a rapid loading, but you're making vacancies. And so both may play a role in why you get the excess heat. And we'll go more over this tomorrow. We use a slightly different system of co-dep than Spay Wars, and we'll talk about that tomorrow. And what we find is, as we do the co-dep, I find that the excess power gain goes up. Anyway, and also we find that as we grow the co-dep layers, they go up. So here, for example, my excess power goes up to above 2.5 watts with an input of 6. And you might say, wow, that's a lot. It is, but it's 2.5 to 6, and I'm looking for 6 out for 0.1 in. But we'll come back to that later. There are 3 possible regions where there may be cold fusion reactions. It may be on asperities, but I think we get hot fusion-like reactions there. It could be right on the surface where we generate these co-deps, and it could be deeper in the metal, 40, 50, 100 microns deep. The other reason I think that there's multiple sites is when we look at heat after death, and when I look, so here we're shutting off the applied electric field intensity. We see that the excess heat that's coming out has different regions, and that's another reason I think there might be different reasons within it. Nickel, I'm going to let Peter talk about nickel. Nickel is very tough to get deuterons into. Look at the diffusivity here compared to palladium. Anyway, at the end of the day, if you get the loading, if you have the active material, if you get the flux, you get the activation energy, you keep the quenchers away, it's not that hard. I mean, I think the amount of effort's about equal to a kidney transplant. I mean, it can be done. You're not going to do it without some practice. You shouldn't do it without some practice, but it takes a bit of effort. And I think that's the level where cold fusion's at. Anyway, here's our gains at the end of the day. Voila, we're getting very high. I think there are several theories to call. I actually think there's a lot of good theories we use here. The fuson theory sort of just assumes that the energy from here to here goes coherently to the flames and the lattice. Okay, and Peter is very. I think he is so close to describing the energy transfer that is what's going on here. We are seeing the lattice heat up beyond what we expect by the Poynting vector, V times I. When we're putting in the electric current, it's essentially DC. So I don't subtract the thermoneutral potential. There are many people in the field that don't. I don't. To me, input power is V times I. It's because I was trained at MIT. That's input power. You don't subtract anything. So it could be that the numbers I'm going to be showing you this week are the lower limit. We actually be getting more power out. If it really should be I times V minus 1.4 or something, that means I'll be showing you the lower limit. We can skip the fuson theory. Oh, the reason I like the fuson theory, it also explains why the neutron branch is not available. The neutron branch is an MeV above here. We only have 1/20th, 1/25th of an electron volt in the picture. So from my way of looking at it, hot fusion lifts all of the forbiddenness. I mean, helium-4 never should be emitted anyway. It's spin forbidden. So if they're getting it at hot fusion, it's because the forbiddenness is lifted. And it could be at millions of degrees. It just doesn't matter anymore. But we see that at cold fusion. And at room temperature, I think that's why we're seeing these branches. Anyway. Again, you'll have that. You'll have all these papers if you send me the email. Okay, let me go to the next one. Questions? No? Please. Yeah.
The geometry of all of this stuff. I mean, you showed some interesting illustrations of the geometry. Can you talk a little bit more about that?
I will. I will. This was just a survey. I just wanted to show you sort of a little bit of what we're going to see for the next 3 days.
You know, well, I'm not going to be here for the next 2 days, so
Okay.
if you can just give me a little précis, I'm actually going to.
Well, what do you mean by geometry?
Well, the lattices and the cubic, the octahedron, you know, all of those different things.
I think you're in big trouble because Peter's going to talk about that tomorrow. You better be here for that. That's important.
So tomorrow.
I mean, really, that's days worth of talk. I can't just answer that in a simple question. That's everything.
I'm actually going to RISD tomorrow to work with a class on design science where we're going to be doing dissections of cubes and things like that. So I have a conflict with that.
Well, if you can't come, a lot of these talks were on the video too. Maybe that'd help. I'm going to just talk a little bit about electrochemistry before I get to calibration. Electrochemistry starts with gold. Certain metals we think do not corrode. Actually, they do. As I pointed out to Barbaros in '92, we were getting, even though we were using a gold anode, gold particles crud on the surface of the cathode. And they were giving a small amount of excess heat. At LENR2, I reported about 7 to 15% excess with a wide band, including going below zero when we had the contaminants. But short of that, what happens is, you know there are these activities. And so if you put two metals together, you're always going to get a voltage. And you're going to get one to corrode, that'll be the anodic. And you'll get one where you have either a deposition of the metal or you'll get hydrogen evolution. So what happens is if we take two metals, there's a cathode and an anode. The voltages come together. This is our corrosion current. And Nernst worked out the Nernst equation, and I hate it. And the reason I hate it is what you do with the Nernst equation is you do your experiment, and then you plug it into the equation and figure out what the activation energies were to make everything come out. To me, that's not engineering. Engineering is I write down the equation, I predict what's going to happen, I get pretty close, maybe add a few terms to the equation. So I find there's two problems with this. One is it's not predictive. Two, it doesn't work when you're outside equilibrium. And I believe that all cold fusion reactions work outside equilibrium, as I'll show you later. Okay, so what we look at is closer to dielectric spectroscopy. And let's take an applied electric field intensity. You know, you have an E field, the electrons go one way, the holes and the cations go the other. And so we have a whole introductory electrical engineering. And if you want to know background, just pick up any ham radio, handbook, and you'll be able to catch up. In fact, MIT has the courses on the internet now. I mean, everything's available. So we can calculate resistance. And water, you see, here's our ultra pure water here. It's 18 megohms. And where people normally like to run cold fusions over here. And as I'll show you tomorrow, that usually kills the reaction. We can skip all this. Polarization. When we put an electric field on something, if it's a charged material, let's say or it has an electric dipole, collagen. That's the reason we form fingers. The reason we form fingers in our spinal cord is collagen self-assembles. It's like magnetic, but it's electric. It's ferroelectric. So when you put on an applied electric field, materials can organize, things can separate, you get polarization. But it also gives you, in addition to electronic and ionic, and I just told you dipolar, polarization, space charge, it gives you dissipation. So these two things are linked. Here we're having the polarization effects, but it turns out they're connected through Hilbert spaces. It turns out where whenever you have a polarization, you're also going to get a dissipation. And that is the basis of dielectric spectroscopy. So here I am back in 1967 doing the same thing I'm doing now, almost with the same equipment. And here I'm working on ordinary water. So we were growing ice crystals at -20 and what used to be building 20, an expendable building, and coming back upstairs here and measuring the properties of water. And the reason that's interesting, I'll get to in a second. Now, this is the electromagnetic spectrum. Gamma rays are up here. This is penetrating ionizing radiation. People say, well, cold fusion doesn't put out radiation. Well, it does. It puts out infrared. It puts out microwaves. Even recently, there's some data, it puts out radio waves. So when we talk about ionizing penetrating radiation, it's up here. But really, we're giving out heat. And I mentioned to you, I showed you pictures of the near infrared. That's down here. And nobody knows about whether cold fusion's putting out here, but I just bought some detectors, so we'll know by the next class. When we measure, well, we can skip all this. Though it would be good to do water, just so you see it once. Water. This is water spectrum from 10 to the 12th down to 10 to the 15th hertz. And here it's from 10 to the 15th down to kilohertz. And what's interesting is let's say we slow water down by freezing it. We can see a little bit more about it. What happens is as we do, there are several spectra that appear in water. And when we plot as a function of temperature, we see that they have different characteristic times. Now, this is where the high dielectric water comes from. And you might want to know this because if you're going to do a Fleischmann-Pons cell, I mean, really, that's where you're getting the deuterons from. That's what's going to make you work or fail. And what happens is when you put on an applied electric field intensity, say this proton or deuteron will flip to here. Now you have two. You have a double defect, so this one comes down here. What happens is they end up diffusing down, and you end up having, I wish, here's the drift ellipsoid. What normally happens is these will just form a sphere and then meet their counter particle and disappear. But the applied electric field intensity makes it where these separate. And that is why water has a high dielectric constant. Questions? All right, we're ready for calibration. Am I going too fast? Too slow. No questions? Okay. Before we talk about the excess heat, I want to show you how we calibrate. So, I'm not sure why this slide is here. Do you know about Semmelweis? If you don't, I'll make a quick. Huh? Semmelweis told doctors to wash their hands. The puerperal, that means close to giving birth, death rate back at that time was around 35%. So if you're a physician, or more likely a midwife, delivering a woman, 1 in 3 of them died right in front of you. He found when he washed his hands, it dropped to 1 in 5. He published it. He eventually found out if he used carbolic acid, he could get it below 1%. So they put him in a psychiatric prison and killed him 18 days later. See, we've been lucky. We've been lucky. I mean, okay. So there's many types of calibration. And let's talk about temperature. Temperature does not tell you how much heat there is. It goes back to Fahrenheit. Let's take this. Here we had a nickel ordinary water system. We ran at 156 watts. It turns out without the control, you don't know what it is. This is what we see in the internet, things like porosity and stuff. I don't like it because there's no control. It makes heat. Everything makes heat. That doesn't tell you whether there's excess heat. But now, if we add a control, we can compare the two. This is a key important thing to do. Heat. It's related to temperature by the specific heat and the mass of material. Okay. And the reason that's important is temperature doesn't tell you how much heat's there. All of these things are obvious to you, so I won't even bother to read it there. We make the measurement by thermal conductivity. What we try to do is set up a good geometry experiment where we are essentially keeping most of the heat inside the reactor and letting small amounts go out. So we're looking at the temperature rise, the mass and specific heat, and we're also measuring what comes out. And if you add those up, that's how much heat's coming in. And we know, it turns out Ben Franklin was the first one to describe thermal conductivity. You should read about when he wasn't busy discovering the current going across the Atlantic, he was doing this experiment. That was a great trip for him. I don't really want to go into the math of this, but basically, the math is complicated unless you make it good geometry. If it's in good geometry, it's quite easy to do, and that's what we do here. But you don't have to. Ways of measuring heat: you could measure the change of phase of ice, which was done initially. Lavoisier, people say, calorimetry is too hard. Nobody can do calorimetry. Lavoisier named oxygen. I dug up his paper for my undergrad thesis here back in '68. And in 1777, before they cut his head off, well, not for that, but because he was a tax collector as well, but he named oxygen. It means acid former. And what he did was he measured the difference in heat capacity, specific heat, between arterial blood and venous blood of the animals. Imagine that, 1770, no refrigerators. I mean, they just had the barest of thermometers, and he was able to measure the specific heat difference. We are way ahead of that. So we have no trouble doing it. All of our systems work this way. We take a mass, a volume that's well characterized. We characterize the surface heat loss by using our aroma controls. We put in a fixed amount of energy, a fixed power over a given amount of time. Usually a square wave is what I like to use. And then we look at the rise of temperature. And that's basically how it is. Now, some of our stuff is multiple rings. So we'll do the heat in the center, and then we'll do the calculations using this in here, and then do a second calculation this and here. And that way, that's another way of getting verification with multiple rings. Okay. Typically, we measure input power as V times I. I do not use the thermoneutral potential. We have great accuracies on these. And also for the current, when we use the dual calorimeter, we're using them in series, electrical series. So we drop any errors between the two even more. Our Nyquist measurements are at least 1 per second. Some people in the field are measuring once every 5 minutes, but if you do it, you may as well do it in a hertz. This is our definition of power gain. Told you that. I showed you the importance of noise power measurement. This is one of our setups. This was that was a long time ago. Basically, this device, this was for the fusors. This transfers the power from the fusor to the ohmic control, fusor to the ohmic control. So what we'll do is we'll often shield, when we have high voltage measurements, we'll put it into an electrometer first. And that's why you see all the electrometers there. And as I'll show you over and over, the minimum we do now is we'll look at delta T over power in, heat flow over power in. So these are separate sensors. We'll do the full bore calorimetry where we calibrate it by using the ohmic control. And these other things, we do a lot of false positives. And again, as I mentioned, serially, what we'll do is we'll measure electricity, we'll do downline calorimetry. Often what we'll do is in addition to the Stirling engine, I'll do calorimetry of the engines, and that'll give us even more data. Can't get enough controls. Okay, we did all that. I told you about the thermal waveform reconstruction. If you do the experiments, you want to do a long initial baseline, at least 8 or 9 hours. And by the way, if you do gamma measurements, it should be 2 weeks, because there could be other things coming in. But for thermal measurements, we'll often do baseline of hours, and then we'll just do a lot of things. We'll just do multiple measurements. This was the measurement that I told you about of adding the heat term. There's a plus term. It's T1 minus T2, but there's a second term, T1 plus T2. Take a look at that paper because this adds the terms in. Anyway, when you do it and get done, you can do this thermal calorimetry both ways. One last point, I don't like flow calorimetry. A lot of people in the field do. And the reason I don't like flow calorimetry is often it's not horizontal. If flow calorimetry is horizontal, always, you're okay. But if there's any vertical component, Defcalian had a vertical component, Rossi has a vertical component, I don't trust it. And the reason is Bernard instability. What happens is, if you have a body of water that's hot on the bottom, the water's going to rise. And so you're going to get a false positive, always. I mean, if any of you have Aquaria at home, go measure the bottom of the aquarium to the top of the aquarium. You'll find the top is hotter. You don't have excess heat in your aquarium. I mean, I don't. So there are ways around it, which is, as it turns out, you can write the equations and you can correct using these corrections. You'll have those in your mailbox too if you send me the email. But other than that, I would avoid flow calorimetry. Anyway, the take-home points. Avoid the Bernard instability of vertical flow calorimetry. Measure your noise, minimize the noise error and artifacts. Fix your analytical calculation by adding the T1 plus T term that people don't like to do. Controls, controls, controls. You can't get enough of them. And that's it for this part. Questions? Yes.
Could you give us any highlights on your progress with the radar over the last year?
Yeah. Want to turn that off?
We're gonna stop broadcasting. All right, that's it.